let's go through the introduction. So positive integers, negative integers, irrational numbers and fractions are all examples of real numbers. In other words, we can say any number is a real number except complex numbers. Now what are complex numbers? So the numbers where you are writing square root of a negative number. For example, square root of minus 15, that is considered as a complex number. Some examples of real numbers include 1, 1 by 2, 1.75, root 2 and so on. Any real number can be plotted on the number line. Now let's discuss classification of real numbers. Real numbers can be further classified as rational numbers and irrational numbers. So it is the union of rational numbers and irrational numbers. For example, we can say rational numbers are the numbers which can be written as in the form of p by q, where q should not be equal to 0. If you are writing a number in the form of numerator upon denominator and the denominator is never equal to 0, we will call such numbers as rational numbers. For example, 3 upon 4, minus 1 upon 2, 7 upon 3. These all are considered as rational numbers. And examples of irrational numbers are the numbers which cannot be written in the form of p by q, okay, where denominator is not equal to 0. These kind of numbers are called as irrational numbers. You cannot write down in the form of p by q. For example, root of all prime numbers. You can say root of 2, that is an irrational number. Root of 3, root of 5, or you can say pi. Pi is also an irrational number. Now, rational numbers is basically the union of non-integer numbers and integers. Now, what are non-integer numbers? So, the numbers where you have decimal expansion. For example, 0.7, right, 0.32, 0.5, they all have decimal expansion, so they are called as non-integer numbers. Whereas integer numbers are the numbers where it is a combination of negative numbers, 0 and positive numbers. So you can say minus 1, 0, 1, they all are the examples of integers. Now what are integers a combination of? It is basically collection of negative numbers along with the whole numbers. So negative numbers you can consider it as minus 1, minus 2, minus 3. These all are the examples of negative numbers. Now talking about whole numbers, so the numbers starting from 0 onwards, 0, 1, 2, 3, they all are whole numbers. Some examples of that include 0, 1, or you can say 100 also. So these are the examples of whole numbers. Now whole numbers basically constitute 0 as well as all the natural numbers. So 0 along with all the natural numbers. What are natural numbers? Basically they are counting numbers. So they will start from 1 onwards, 1, 2, 3, 4, so on. Okay. So some examples of natural numbers include 1, 2, 99. They all are examples of natural numbers. First of all, we are going to divide 17 by 6. So let's proceed. Here 17 is my dividend, 6 is the divisor. So 6 into 2, we are going to get 12. A multiple of 6 which is lesser than 17. So we are going to get the remainder as 5. Now here, what is dividend? The number that you are dividing, 17. What is divisor? That is the number with which you are dividing. Quotient is the result that you are getting after division process. And the remainder is the number that is left out after division. So here, 17 is our dividend, 6 is the divisor, 2 is the quotient and 5 is remainder. This is our next example. We have to divide 5 by 12. Now here, what is different is the dividend is lesser than the divisor. Now in such cases, what will happen? Since 5 will not come in the table of 12, we have to multiply 12 with 0 in order to get 0 over here, and hence we are going to get remainder as 5. So in this process, we obtain that dividend is 5, divisor is 12, quotient is 0 and remainder is 5. Now let's go through the third example. Here we have to divide 20 by 4. So 20 is our dividend, 4 is the divisor. Now in the table of 4, we get 5 times 20. So 5 is our quotient and the remainder that we are going to obtain after division process would be 0. With these three examples, let's discuss what is Euclid's division lemma. First of all, what is lemma? It is a proven statement that is used for proving another statement. A lemma is a proven statement that is used for proving another statement. A statement which is already proven to be true and that you are using to prove something else. So we have been learning throughout dividend equals to divisor into quotient plus remainder in our previous classes. What it is? Given positive integers. Remember, the integers have to be positive. A and B, there exist unique integers. It cannot be different integers. There will be existing unique integers Q and R satisfying A equals to BQ plus R. Now what is A here? A is the dividend. What is B? B is our divisor. Q is the quotient and R is our remainder. Now the condition that is followed here is R is greater than or equal to 0 but lesser than B, which means that remainder is greater than or equal to 0 but it will always be lesser than the divisor. Now we are going to go through all those three examples and write down it in the terms of Euclid's division lemma. First of all, 17 is equals to 6 into 2 plus 5. We can say 6 goes into 17 twice and leaves a remainder 5. In the second example, we discussed that 5 is equals to 12 into 0 plus 5. Now here, observe that the quotient is 0. The reason being, dividend is lesser than the divisor. So this relation holds since 12 is larger than 5. In the third example, we observe that 20 is equals to 4 into 5 plus 0. Now what is different here? The remainder is 0. Here 4 goes into 20 5 times and leaves no remainder. So that is, for each pair of positive integers A and B, we have found whole numbers Q and R satisfying the relation A is equals to BQ plus R, where R has to be greater than or equal to 0 but less than B. So it means that dividend will always be equals to divisor into quotient plus remainder, and the condition is remainder has to be greater than or equal to 0 but less than divisor. Now the final point that we are going to note here is Q, which means quotient, or R, which means remainder, can also be 0. Q or R can also be 0. We are going to discuss Euclid's division algorithm. So you might be wondering, what is algorithm, right? An algorithm is a series of well-defined steps which gives us a procedure for solving a particular type of problem. Now what is Euclid's division algorithm? It is a technique with the help of which we can calculate highest common factor HCF of two given positive integers. So let's take the two numbers 6 and 18. Now what are the factors of 6? They are 1, 2, 3 and 6. What are the factors of 18 now? 1, 2, 3, 6, 9 and 18. Correct? Now what are the common factors of both of them? 1, 2, 3 and 6. So these are the common factors of 6 and 18. But among them, what is the highest common factor? 6. Right? So 6 is the highest common factor of 6 and 18. We can write down HCF of 6 and 18 is equals to 6. Now, this process is very time consuming. So, this Euclid's division algorithm will give us a technique with the help of which we can easily calculate highest common factor of two given positive integers. Now, let's find the HCF of 455 and 42. Here, 455 is greater than 42, right? So, therefore, we will take 455 as our dividend and we will try to divide it with 42. On division, we will get 10 as our quotient. So, we will write down 42 into 10, that would be 420 here. On subtracting, we will get a remainder of 35 here. So in terms of Euclid's division lemma, how could we write down this? Remember, for 455 is our dividend, 42 is the divisor, 35 is the remainder and 10 is the quotient. So we will write down 455 is equals to 42 into 10 plus 35. Dividend is equals to divisor into quotient plus remainder. Now, we did not get remainder as 0. So, what are we going to do now? We'll consider 42, which is the divisor, and remainder 35 and apply the division lemma again. So, while applying the division lemma again, here 35 will be our divisor and 42 will be our dividend. So, 35 divisor and 42 dividend. 35 into 1, we are going to get 35. On subtracting, we will get a remainder of 7. So, still we have not got the remainder as 0. We will write down 42 dividend is equals to divisor 35 into quotient 1 plus remainder 7. Now we will consider divisor 35 and remainder 7 and apply the division lemma again. So while applying that, 7 will be our new divisor and 35 will be our new dividend. 7 5s are 35. Now at this step we got the remainder as 0. So according to Euclid's division lemma, we will write down the statement as 35 is equals to 7 into 5 plus 0. At this process, we will stop the division algorithm. Notice that the remainder has become 0 and we cannot proceed any further. So, at the last step, when you will get the remainder as 0, you will stop your procedure over there. You will not go further. We will claim that the HCF of 455 and 42 is the divisor at the last stage when we got the remainder as 0, that is 7. So, what was the last step? We got 35 is equals to 7 into 5 plus 0. At this stage, we got the remainder as 0, right? So, at this stage, the divisor is 7. That is the reason we are taking HCF as 7. So, HCF of 455 and 42 is equals to 7. So let's discuss all the steps of Euclid's division algorithm. To obtain the HCF of two positive integers, say C and D, with C greater than D, we will follow the steps given. First step will be apply Euclid's division lemma to C and D. So we find whole numbers Q and R such that C is equals to dq plus r. So C is our dividend here, D is the divisor, Q is the quotient and R is the remainder. The condition that is followed here is R is greater than equals to 0 and less than D, which means remainder is greater than or equals to 0 and less than divisor. So step 2 would be, if remainder is equals to 0, if R is equals to 0, D is the HCF of C and D. If remainder is not equals to 0, apply the division lemma to D and R again. Let's understand this step. So let's say you have two numbers 18 and 6. 18 is greater than 6. Let's do the division. We will get 6 3s are 18. Now at this step itself we got the remainder as 0. So we will write down it as 18 is equals to 6 into 3 plus 0. The divisor at this stage 6 will be the HCF of 6 and 18. So we will write down HCF of 6 and 18 is equals to 6. Now what happens if the remainder is not equals to 0? Let's take another example. 42 and 35. Now here if you will observe, you are going to get 35 into 1, 35 here, and the remainder you are going to get as 7. So remainder is not equals to 0, right? We'll apply the division lemma again, considering 7 as the new divisor and 35 as the new dividend. So 7 into 5, we are going to get 35 here. And hence, now your remainder is equals to 0. So here we will stop. Now observe here the steps. 42 is equals to 35 into 1 plus 7. In the first step, we did not get the remainder as 0. That's why we are repeating the step again. What are we doing now? We are taking 35, which is the divisor of the previous step, as the dividend, and 7, which is the remainder of the previous step, as divisor. We are multiplying 7 with 5. We will get remainder as 0 in this case. So here we will stop our procedure, and at this stage we will consider the divisor, which is 7, as the HCF of 42 and 35. So HCF of 42 and 35 will be equals to the divisor at the last stage, which is 7. So the third step was, we will continue the process till we get remainder as 0. The divisor at this stage will be the required HCF. We are going to solve exercise 1.1, question number 1. Let's read out the question. Find the HCF of two numbers by using Euclid's division algorithm. Now this is the first subpart of question number 1. Find the HCF of 135 and 225. Observe here, 225 is greater than 135. So we are going to take 225 as our dividend, and 135 we will take it as our divisor. Multiply 135 with 1, we will obtain 135. Let's subtract 225 minus 135. We will get 90. So on division, we are getting a remainder of 90. Let's write it down in terms of Euclid's division lemma. So 225 is equals to 135 into 1 plus 90. We have written dividend is equals to divisor into quotient plus remainder. Now since here remainder is not equals to 0, therefore we will apply Euclid division lemma to 135 and 90 again. Here we will consider 90 as our divisor and 135 as our dividend. So what are we doing? We are considering the divisor of the previous step as our dividend here and the remainder of the previous step as our divisor. So multiplying 90 with 1 will give us 90, which is lesser than 135, and hence we are going to get a remainder of 45. So our next step would be 135 is equals to 90 into 1 plus 45. Here observe, remainder is equals to 45, right? And since remainder is not equals to 0, therefore we will apply the division lemma to 90 and 45 again, considering 90 as our dividend now and 45 as our divisor. So let's do the division. 90 divided by 45. 45 into 2 will give us 90. On subtracting, we will get a remainder of 0. So this is the step where we got the remainder as 0. We will write it down as 90 is equals to 45 into 2 plus 0. Now in this step, we got a remainder equals to 0. Since remainder is equals to 0 now, we will stop our process. And the divisor at this stage is 45. So the highest common factor of 225 and 135 will be equals to the divisor at this stage, which is equals to 45. Now this is the second subpart of question number 1. Find the HCF of 196 and 38,220. Considering 38,220 as our dividend and 196 as our divisor. The reason is 38,220 is greater than 196. Now multiply 196 with 1. We'll get 196 over here. On subtracting 196 from 382, we'll get a remainder of 186. Bring the 2 down. So we are now with 1862. We want a multiple of 196 which is lesser than or equal to 1862. Let's multiply 196 with 9. We will obtain 1764. Let's subtract now. So if you will subtract 1764 from 1862, we'll get a remainder of 98. Now we need to bring the 0 down. So we will have 980 now. Multiplying 196 with 5 will give us a multiple of 196 as 980. And on subtraction of 980 from 980, we'll get a remainder of 0. Now, here it is a case where we got a remainder of 0 just in the first step itself. So, how are we going to write it down? We will write down 38,220 is equals to 196 into 195 plus 0. Now, since remainder is equals to 0, therefore the process stops here. Divisor at this stage is 196. Therefore, HCF, highest common factor of 38,220 and 196 will be equals to 196. Now this is the third subpart of question number 1. Find the HCF of 867 and 255. Now it's very evident that 867 is greater than 255. So we will try to divide 867, considering it as dividend, with 255, considering this as divisor. Now, multiply 255 with 3 because we want a multiple of 255 which is lesser than or equals to 867. On multiplying 255 with 3, we will get 765. Now, subtracting 765 from 867, we will get a remainder of 102. So, the remainder is not equals to 0 here. We will write it down as 867 dividend is equals to 255 divisor into 3 quotient plus 102 remainder. Now, in this step, we got remainder as 102 which is not equals to 0. Therefore, we will apply division lemma to 255 and 102 again, considering 255 as our dividend and 102 as our divisor. So what do we do here generally? The remainder of the previous step, we consider it as our divisor in the next step. And the divisor of the previous step, we consider it as dividend in the next step. And this happens only when the remainder is not equals to 0. Now, multiplying 102 with 2 will give us a multiple 204, which is lesser than 255. On subtraction, we'll get a remainder of 51. So, we will write it down as 255 is equals to 102 multiplied with 2 plus 51. Now, since remainder is equals to 51, which is not equals to 0, therefore, we will apply division lemma to 102 and 51 again, considering 51 as our divisor and 102 as our dividend. Now, let's divide. So, 51 into 2 will bring us 102. On subtraction, we are going to get a remainder of 0. So, here is our last step. Since we got the remainder as 0, we will write it down. 102 is equals to 51 into 2 plus 0. Now, since the remainder is equals to 0, therefore, we will stop the process over here. And the divisor at this stage is 51. So, the highest common factor of 867 and 255, we will consider it as the divisor of the last stage, which will be equals to 51. Question number 2 of exercise 1.1. It says, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Let's look at the solution. So first of all here, we will take a as a positive integer. Let a be any positive integer. And the divisor b is equals to 6. Now if divisor is equals to 6, what are the possible remainders? So we can say by Euclid division algorithm, a is equals to 6q plus r for some integer q which is greater than or equals to 0. Here what is q? Q is the quotient. And for b equals to 6, the possible remainders would be r will be equals to either 0, 1, 2, 3, 4 or 5. These are the possible remainders for divisor equals to 6 because r is always greater than or equals to 0 and less than 6 as per Euclid's division lemma. We will consider the first case now. In case 1, you can observe that we can write down a is equals to 6q plus 0. Here r we are considering it as 0. So 6q plus 0 can be written as 6q, which can also be written as twice of 3q. Now we can observe that in first case, we can write down this a value as 2 times of some factor, 2 times of 3q. Therefore, this is definitely even. The reason being a is divisible by 2. Therefore, twice of 3q is actually even value. Now in the second case, we can observe that we are taking the remainder as 1. So a will be equals to 6q plus 1. Now here 6q can be written as twice of 3q plus 1. Now observe here, we have 2 which is multiplied with some value, let's say k, and we are getting a remainder of 1. So which basically indicates that this a value 6q plus 1 is not an even number. Otherwise we would not have got any remainder, right? Since we are getting a remainder of 1, therefore it is an odd integer because it is not completely divisible by 2. Now the third case here says that a is equals to 6q plus 2. Here what are we doing? We are considering r is equals to 2 here. Now in this case, what can we do? We can take 2 common from both of them and we can write it down as twice of 3q plus 1. So here we can observe that this a can be written as 2 multiplied by something, right? So here we are not getting any remainder as such. Therefore, it is an even integer. Now let's discuss case 4. So in case 4, what are we doing? We are considering remainder as 3. Therefore, a can be written as 6q plus 3. Now this 3 we are trying to write it down as 2 plus 1. So this 6q plus 3 entirely we are writing it down as 6q plus 2 plus 1. Now from these two values 6q plus 2, what are we doing? We are taking 2 common. So we will obtain twice of 3q plus 1 and this plus 1 will be written afterwards. So here you can observe that we can write down this entire expression as twice of a plus 1, which basically indicates that if we will try to divide this entire number with 2, we will get a remainder of 1, which means this is not completely divisible by 2, right? So therefore it is an odd integer. It is an odd integer. Now let's look at the case 5. In case 5, we can observe that we are taking the remainder as 4. So we are writing a equals to 6q plus 4. Now in this entire expression, it is easy to take 2 outside as a factor. So we can write it down twice of 3q plus 2. Now this entire number is exactly divisible by 2 because we are not having any remainder as such, right? So therefore it is an even integer. Next comes case 6. So here what are we doing? We are taking the remainder as 5. Therefore a can be written as 6 cube plus 5. Now this plus 5 we will try to break it down as 4 plus 1. So we will write down 6 cube plus 4 plus 1. Now from this 6 cube plus 4 we will take 2 common outside. So that can be written as twice of 3 cube plus 2. And this plus 1 which is present over here will be written afterwards. So this entire expression can be written as twice of k plus 1. So what did we observe? On dividing this number by 2, we are getting a remainder of 1. Therefore, this number is not completely divisible by 2 and hence it is an odd integer. So we have discussed total 6 cases where we started with r equals to 0, r equals to 1, r equals to 2, r equals to 3, r equals to 4 and r equals to 5. And in all the 6 cases, sometimes we got the integer as an even integer and sometimes we got it as an odd integer. So clearly we can see that 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5, they are of the form twice of k plus 1, where k is an integer. So they are actually not divisible by 2 and hence we can write down any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, where q is some integer. Exercise 1.1, question number 3. It says an army contingent of 616 members is to march behind an army band of 32 members in a parade. So observe here, an army contingent of 616 members, they are marching behind an army band of 32 members in a parade. Now these two groups, the two groups are to march in the same number of columns. This is very important, in the same number of columns. Now they are asking what is the maximum number of columns in which they can march. So there are 32 band members. Behind them there is an army contingent of 616 members marching behind 32 members. So we have to find out if both of them are marching in the same number of columns, then what is the maximum number of columns in which they can march? Let's look at the solution. So since 616 is greater than 32, we will consider 616 as our dividend and 32 as our divisor. Now let's multiply 32 with 1. We'll get 32 here. On subtracting 32 from 61, we'll get 29. Now we are going to bring this 6 down in order to make it 296. So we want a multiple of 32 which is less than or equals to 296. Let's multiply 32 with 9. So we will get 288. Now on subtraction, we will get a remainder of 8. So after dividing 616 with 32, we observe that we are getting a remainder of 8. Hence, we will write it down as HCF of 616 and 32 will give us maximum number of columns in which they can march. So using Euclid's division algorithm, we can find out highest common factor. And since after division we got a remainder of 8, we will write it down as 616 equals to 32 into 19 plus 8. Now in the next step, since remainder is not equals to 0, we are going to repeat this procedure again of division, considering 8 as our divisor now and 32, which is the divisor of the previous step, we will consider it as our dividend now. So 8 fours are, we will get 32 and on subtraction we will get a remainder of 0. So hence we observe that in this step we are getting a remainder of 0. Now since remainder was not equals to 0 in the previous step, we applied division lemma to 32 and 8, considering 32 as our dividend and 8 as our divisor. And hence after division we got a remainder of 0. So we will write it down as 32 is equals to 8 into 4 plus 0. Now here we got the remainder as 0. So since remainder is equals to 0 over here, the process of division will stop. And hence the divisor at this stage is 8. Therefore the highest common factor of 616 and 32 will be equals to 8. And hence the maximum number of columns in which they can march, it will be equals to 8. So therefore they can march in maximum 8 number of columns.
Question number 4 of exercise 1.1. The question is, use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So observe here, we have to take the square of any positive integer and we have to express it in the form of either 3m or 3m plus 1, where what is m? M is some integer. Let's go through the solution now. First of all, we will consider a to be any positive integer, and for a the divisor b is equals to 3. So we can say by Euclid's division algorithm, a is equals to 3q plus r, where 3 is our divisor, q is the quotient, r is the remainder. And over here a that we have considered as a positive integer, it is our dividend. Q, which is the quotient, its value is an integer which is greater than or equals to 0. The possible values of remainder r would be equals to 0, 1 and 2, because according to the condition, r has to be, the remainder has to be either greater than or equals to 0 and less than 3, less than the divisor. So let's look at the first case. Here we are considering remainder to be equals to 0. So we will write down a as 3q plus 0, which can be written as 3q. Now we have to take the square of this positive integer a. So on taking a square on both the sides, we will have a square is equals to 3q whole square, which will give us a square equals to 3q whole square will become 9 times of q square. Now from this we can take 3 common and write it down as 3 times of 3q square, which can also be written as 3 times of m, where m is some integer. So now we are left with two cases when remainder is equals to 1 and remainder is equals to 2. Let's look at those. So in case 2, we are considering remainder to be equals to 1. In that case, we can write down positive integer a as 3q plus 1. On taking a square on both the sides, we will obtain a square equals to 3q plus 1 whole square. Now, how to evaluate this? So we will be using a plus b whole square identity, which says a square plus 2ab plus b square is the expansion of this. Now over here, if we will compare 3q plus 1 whole square with a plus b whole square, our a over here is 3q and b value is 1. So we will substitute this in the expansion and we will obtain a square is equals to 3q whole square plus 2 into 3q into 1 plus 1 whole square. Let's simplify this. So we are going to get 3q whole square as 9q square plus 2 into 3q into 1 will give us 6q plus 1 whole square will give us 1 itself. Now, it is time for us to take 3 common. So we can take 3 common from the first two terms, 9q square plus 6q. This plus 1 will remain as it is. So we will be writing a square is equals to, taking 3 common from 9q square and 6q, we will write it down as 3 into 3q square plus 2q plus 1. So this entire expression 3q square plus 2q can be substituted as m. So we will write down finally as a square is equals to 3m plus 1. So in the second case, we observed that the square of any positive integer, we are able to write it down in the form of 3m plus 1. Now let's look at the third case where remainder is equals to 2. So in case 3, we will write down the positive integer a as 3q plus 2. Here remainder is equals to 2. So if you will take a square on both the sides, it will become a square is equals to 3q plus 2 whole square. Now same way we will be using the identity a plus b whole square in order to evaluate this. Over here if you will compare, a value we will consider it as 3q and b value we will consider it as 2. So on doing the expansion of this term, we will obtain a square is equals to 3q whole square plus 2 into 3q into 2 plus 2 whole square. On simplifying this, we are going to get a square is equals to 3q whole square will give us 9q square, 2 into 3q into 2 will give us 12q and 2 whole square will give us 4. Now, is it easy to take 3 common? We can't take 3 common from 4, right? So what we will do? We'll split 4 in terms of 3 plus 1. Let's do that. So finally we will be writing a square is equals to 9q square plus 12q. This 4 we will split it in the form of 3 plus 1. Now from the first 3 terms 9q square plus 12q plus 3 we can take 3 common, right? So we'll write down a square is equals to 3 times of 3q square plus 4q plus 1. And this plus 1 which is afterwards, it will remain as it is over here. So now we can see that we can write down this square of any positive integer in the form of 3 multiplied by some integer plus 1. So let's write it down. Finally, we will be writing a square is equals to 3m plus 1, where m value is 3q square plus 4q plus 1. So these were all the 3 cases where we considered remainder to be equals to 0 in the first case. In the second case, we considered remainder to be equals to 1. And in the third case, we considered remainder to be equals to 2. And in the first case, we obtained the square of any positive integer in the form of 3m. In second case, we obtained it in the form of 3m plus 1. And in the third case, we obtained it in the form of 3m plus 1. So what did we conclude? We'll write it down as clearly square of 3q plus 1 and 3q plus 2 are of the form 3m or 3m plus 1, where m is an integer. Hence, we can conclude that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m.
Question number 5 of exercise 1.1. The question is, use Euclid's division lemma to show that cube of any positive integer is either of the form 9m plus 1 or 9m plus 8. So we have to express the cube of any positive integer in either of these forms, either 9m or 9m plus 1 or 9m plus 8. Let's go through the solution. So here we'll assume a to be any positive integer for which the divisor b is equals to 3. And then by Euclid's division lemma, we can write it down as a is equals to 3 times of q plus r, where a is the dividend, 3 is our divisor Q is the quotient and R is the remainder. For some integer Q which is greater than or equals to 0 and the possible values of remainder are 0, 1 and 2. Because R is greater than or equals to 0 and less than 3, which means remainder is greater than or equals to 0 and less than the divisor. So in the first case, we'll write down A is equals to 3Q plus 0. Here we are taking remainder as 0. So A value will be equals to 3Q. Now we'll take cube on both the sides. So we are going to get A cube is equals to 3Q whole cube. So if we will multiply 3Q thrice, we are going to get A cube is equals to 27Q cube. So what are we doing? We are multiplying 3 times. 3 into 3 into 3, we are going to get 27 and Q into Q into Q will get Q cube. So it's easy to take 9 common from 27Q cube. If we will do so, we are going to get A cube is equals to 9 times of 3Q cube. So we can write down it in the form of 9 multiplied by something. Hence, our final step would be A cube is equals to 9 times of M. So clearly we observe that when remainder is equals to 0, we are able to write down the cube of positive integer A as 9 times of M. Now let's consider the rest two cases where remainder is equals to 1 and remainder is equals to 2. Now in the second case, we are taking remainder equals to 1. So we will be writing A is equals to 3Q plus 1. If we will take cube on both the sides, it will be A cube is equals to 3Q plus 1 whole cube. So how to evaluate this? We will be using the identity which says A plus B whole cube is equals to A cube plus 3A square B plus 3AB square plus B cube. So, using this identity, we are going to expand 3Q plus 1 whole cube, where if you will compare, A is nothing but 3Q and B value we are going to take it as 1. So, A cube can be written as 3Q whole cube plus 3 times of 3Q whole square multiplied by 1 plus 3 times of 3Q into 1 whole square plus 1 whole cube. So if we will simplify this entire expression, we will get A cube is equals to 3Q whole cube will become 27Q cube. 3 into 3Q whole square into 1 will give us 27Q square, because 3Q whole square will become 9Q square. When 9Q square will be multiplied with 3, we are going to get 27Q square. Multiplied with 1 will lead us to again 27Q square. Now 3 into 3Q, 9Q, and 9Q into 1 whole square will again give us 9Q only plus 1 whole cube. So the cube of 1 will be again plus 1 only. Now finally we are writing A cube equals to, from the first 3 terms, 27Q cube plus 27Q square plus 9Q, we are going to take 9 common from all of them. Hence we can write down 9 times of 3Q cube plus 3Q square plus Q. And this plus 1 we are going to keep it as it is over here. So it's easy to write down it in the form of 9 multiplied by something plus 1. So finally we will be writing A cube is equals to 9 times of M plus 1. So easily in the second case, what did we observe? When we considered remainder is equals to 1, we got the cube of any positive integer as in the form of 9m plus 1. Now let's consider the third case where remainder is equals to 2. So in the third case, we will be writing a equals to 3q plus 2, where remainder is equals to 2. So if we will take the cube on both the sides, we will be writing a cube is equals to, we will be writing a cube is equals to 3q plus 2 whole cube. Now this, how to expand it? Again we will be using a plus b whole cube identity, which is a cube plus 3a square b plus 3ab square plus b cube. Now here if we will compare a plus b whole cube with 3q plus 2 whole cube, wherever we will have a, we will be writing over there 3q, and wherever we are having b, we will be writing 2 in that place. Let's expand it. So it would be a cube is equals to 3q whole cube plus 3 multiplied by 3q whole square multiplied with 2 plus 3 multiplied with 3q multiplied with 2 whole square plus 2 whole cube. So simply we have used this identity in order to expand 3q plus 2 whole cube. Now let's simplify it further. We can write down 3q whole cube as 27q cube. 3 into 3q whole square into 2 will give us 3 into 9q square into 2, which will be nothing but 54q square. 3 into 3q into 2 square will be written as 3 into 3q into 4, which is 36q, plus 2 whole cube will be written as 8. So it is easy, if you will observe, to take 9 common from the first 3 terms. Let's take it common then. We will be writing a cube is equals to 9 times of 3q cube plus 6q square plus 4q. Plus this 8 will remain as it is over here. So finally we will be writing a cube is equals to 9 times of m plus 8. So what did we observe in the third case? When we considered remainder equals to 2, we can write down the cube of any positive integer in the form of 9m plus 8. So we observed all the 3 cases where if we are considering r is equals to 0, we were able to write down the cube of any positive integer in the form of 9m. In the second case, when we considered r value equals to 1, we were able to write down the cube of any positive integer in the form of 9m plus 1. And finally, in the third case, when we considered r value to be equals to 2, we were able to write down cube of any positive integer in the form of 9m plus 8. So clearly, cube of 3q, 3q plus 1 and 3q plus 2 are of the form 9m or 9m plus 1 or 9m plus 8, where m is an integer. And hence we can conclude that cube of any positive integer is either of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Fundamental theorem of arithmetic. But before going into that, let's discuss some basics. So what is a prime number? A natural number that can be divided exactly only by 1 and itself, which basically means that a prime number will have only 2 factors, 1 and the number itself. What are the examples of prime numbers? They are 2, 3, 5 and 7. The reason is 2 has only 2 factors, that is 1 and 2 itself. Same way 3 has only 2 factors, that is 1 and 3 itself. Same way 5 has only 2 factors, that is 1 and 5 itself. Similarly 7 has only 2 factors, that is 1 and 7 itself. So if a natural number can be divided exactly only by 1 and itself, we will call such a number as prime number. Now, what are composite numbers then? So a natural number that has more than 2 factors, it will be called as composite number. For example, 4, 6, 8, 9, etc. So we can see that 4 has more than 2 factors. What all are they? 1, 2 and 4 itself. So here you could observe that 4 has 3 factors, 1, 2 and 4. Now let's look at 6. So 6 has 1, 2, 3 and 6 as its factors. So there are 4 factors of 6 that we can observe, right? Similarly, what about 8? So 8 has 1, 2, 4 and 8. These are the 4 factors of 8. Talking about 9, so 9 has 1, 3 and 9. These are the 3 factors of 9. So what did we observe? A natural number that has more than 2 factors, that will be considered as a composite number. Now, what about 1 then? Is it a prime number or a composite number? So, please make a note of it. 1 is neither prime nor composite. So, 1 is neither a prime number nor a composite number, because 1 is not having 2 factors or more than 2 factors. Therefore, it is neither considered to be prime number nor composite numbers. Now, let's go through fundamental theorem of arithmetic. So, its statement is every composite number can be expressed or factorized as a product of primes. Here, primes indicates prime numbers. And this factorization is unique. This factorization is unique, apart from the order in which the prime factors occur. So simply, if you have a composite number, you can write it down in the form of prime factors, and this prime factorization will always be unique no matter what is the order of those prime factors. Now, the prime factorization of a natural number is unique except for the order of its factors. This is the other statement. You can write it down in place of the above statement. So, it is also fundamental theorem of arithmetic. The prime factorization of a natural number is unique except for the order of its factors. Now, let's go through one of the examples to understand this fundamental theorem of arithmetic better. So, we will be finding out the prime factorization of 32,760. So, let's divide 32,760. Now, over here, we could observe that the unit place of this number is 0. So, which means it is divisible by 2. Let's try to divide it. We are going to get the quotient as 16,380. Now again, this number is also having its units place digit as 0. So, it is divisible by 2. Let's divide it with 2. We are going to get 8,190. Now again, for this number also we could observe that its units place digit is 0. So, it is divisible by 2. Let's try to divide it. We are going to get the quotient as 4,095. Now, its unit place digit is 5. So, which means it is not divisible by 2. So, now its unit place digit is 5, which means it is not divisible by 2. So, now the number which is greater than 2 is 3. So, let's try to divide it with 3. We will see that on division with 3 of this number, we are going to obtain the quotient as 1,365. Again, the unit place of this number is 5. So, let's try to divide it with 3 to check whether it will be divisible by 3 or not. If we will try to divide it with 3, we are going to obtain 455 as the quotient, leaving no remainder. Now, observe that this number is neither divisible by 2 nor divisible by 3. So, now the next prime factor we will be taking as 5. If we will divide 455 with 5, we are going to get quotient as 91. Now, what is the number should I take it as prime factor so that 91 will be exactly divisible by that prime factor? So, we will be taking 7 over here. If we will divide 91 with 7, we are going to get 13. Now, 13 is a prime factor, so definitely it is divisible by 1 and itself. So we'll be dividing 13 with 13, we'll get 1. So this is the entire prime factorization of 32,760. Now let's write it down. So it will be written as 32,760 is equals to the product of all the prime factors, 2 into 2 into 2 into 3 into 3 into 5 into 7 into 30, which can be written as 2 cube into 3 square into 5 into 7 into 30. So once we have decided that the order will be ascending, then the way the number is factorized is unique. You can observe that when we were doing the prime factorization of this number, we decided that we will go in an ascending order of prime factors, right? So therefore, we obtain a unique prime factorization. Now, the prime factorization of every composite number will always be unique except for the order in which you are writing those prime factors. We are going to go through this concept that the product of two numbers is equals to the product of their highest common factor HCF and the lowest common multiple LCM. So to understand this better, let's take one example and see how this statement is true with the help of that example. So we will be finding out the lowest common multiple and highest common factor of 6 and 20. Let's do the prime factorization of 6 and 20. We'll write down 6 as, if you will divide 6 with 2, we are going to get 3 over here. Now let's divide 3 with 3, we'll get 1. So the prime factorization of 6 will have two factors, that is 2 into 3. Now how will we be writing down 20? So let's prime factorize 20 now. Let's divide 20 with 2 first of all. We'll be getting 10 as a quotient. Now again 10 is divisible by 2, so we'll divide 10 with 2. We'll get 5 as a quotient. Now this 5 is exactly divisible by 5, so we'll get 1 as the quotient. Here our prime factorization of 6 and 20 stops. Now let's write down 6 and 20 in terms of the product of their prime factors. So 6 can be written as 2 into 3, which can also be written as 2 raised to 1 into 3 raised to 1. Now for 20, we can write it down as 20 equals to 2 into 2 into 5, which can also be written as 2 raised to 2 into 5 raised to 1. Now, what is the highest common factor for these two numbers? So observe, the highest common factor is the factor which is common in between 6 and 20 and which is the highest one among them. So we observe that 6 can be written as 2 into 3 and 20 can be written as 2 into 2 into 5. Now among them, what are the common factors? We have 2 only, and that is the highest one. So therefore, we will be writing down the highest common factor of 6 and 20 to be equals to 2. Now what would be the lowest common multiple? So we will write down all the factors of 6 and 20, and whichever factor is common, we will write it down only once. So the LCM of 6 and 20 would be, see, since 2 is a common factor in 6 and 20, we will write down 2 only once, and rest all the factors we will be writing it down. So 2 into 2 into 3 into 5. So the product of all these numbers will give us the LCM. Hence we can write down LCM of 6 and 20 is equals to 2 into 2 into 3 into 5, which is equals to 60. Now observe here, the product of HCF, highest common factor of 6 and 20, and LCM, lowest common multiple of 6 and 20 is equals to 2 is the highest common factor, multiplied it with lowest common multiple, which is 60. So if you will multiply these two numbers, highest common factor and lowest common multiple, we saw that we are getting 120.
Will it be the same if we will multiply these two numbers itself? Let's check. Yes, if we will multiply 6 with 20, we are going to get 6 into 20 as 120. So we observed here that the product of two numbers 6 and 20 is equals to their highest common factor multiplied with their lowest common multiple. So as a statement, how can we write down? HCF, highest common factor of 6 and 20 multiplied with lowest common multiple of 6 and 20 is equals to the product of the two numbers 6 into 20. For any two positive integers a and b, highest common factor of a and b multiplied with lowest common multiple of a and b will be equals to the product of a with b. So this is how we generalize this entire statement. Highest common factor of any two numbers multiplied with lowest common multiple of those two numbers will be equal to the product of those two numbers itself. Now, how could we use this result? So we can use this result to find out the lowest common multiple of two positive integers if we have already found out the highest common factor of two positive integers. Similarly, we can use this result to find out the highest common factor of any two positive integers if we have already found out the lowest common multiple of two positive integers. And also, if in the question you have been given lowest common multiple and highest common factor and one of the number itself, you can easily find out the other number by using this statement. So, for example, if you have been given in the question that highest common factor of two numbers a and let's say 20 is equals to 2 and lowest common multiple of a and 20 is equals to 60, then you can easily find out the other number a by using this statement that highest common factor multiplied with lowest common multiple of a and 20 will be equals to the product of a with 20. So we will be writing 2 into 60 is equals to a into 20. With this, we can easily find out the value of a. How? 2 into 60, that would be 120 equals to 20a. So therefore, if you have to find out a value, just bring this 20 towards the left hand side. We will be writing it in division with 120. So 120 divided by 20 will give us a, whose value will be equals to 6. So with this, we are able to find out one of the numbers if we have been given other number and the highest common factor and lowest common multiple of those two numbers. So clearly we could observe that a is equals to 6 here. The product of three numbers is not equal to the product of their highest common factor HCF and lowest common multiple LCM. Now let's see whether this statement is true or not with the help of an example. Here we are finding out the LCM and HCF of 6, 72 and 120. Let's do the prime factorization of all these three numbers. Let's start with 6 first of all. So 6, when we will divide it with 2, we are going to get 3 as the quotient. Now we will divide 3 with 3, we will get 1. So 6 can be written as 2 into 3. Now let's look at 72. So if we will try to divide 72 with 2, we are going to get 36. And now 36, if we will divide it with 2, we are going to get 18 as a quotient. Again, dividing 18 with 2 will give us 9 as a quotient. And dividing 9 with 3 will give us 3 as a quotient. Finally, we will divide 3 with 3 in order to get 1. Now, we are going to do the prime factorization of 120. So, let's divide it with 2 first of all. We will get 60. Now, let's divide 60 with 2. We are going to get 30 now
as a question. If we will divide 30 with 2 again, we are going to get 15. Now 15 cannot be divided with 2. So we are going to divide it with 3. 3 5s are 15. Now we will divide 5 with 5 in order to get 1. So here we have done the prime factorization of all these three numbers. Now let's write down these numbers as a product of their prime factors. First of all, we will be writing 6 as 2 raised to 1 into 3 raised to 1. 2 into 3. Then we are writing 72 as the product of their prime factors. 2 into 2 into 2 into 3 into 3. So which can be written as 2 raised to 3 into 3 raised to 2. Now next we are writing 120 as a product of their prime factors. So it would be 2 raised to 3 into 3 into 5. You could observe there are 3 times that we got 2 over here, right? And we got 3 ones and 5 ones. So therefore we are writing 2 raised to 3 into 3 into 5. Now the HCF of these three numbers 6, 72 and 120 would be, we will be writing down the prime factors first of all. So here we could observe that in all the three numbers, here we are not having 5 at all. While doing the prime factorization of 6, we are not having 5 at all. Right? Similarly, in 72 also we are not having 5 at all. In 120, we are having 5 ones. So, in the HCF, we will not include 5 at all because 5 is not the common factor of these three numbers together. Now, what we will be writing as HCF? So, we will write down 2 raised to 1 into 3 raised to 1 because 2 raised to 1 is present in 6. Here it is 2 raised to 3, so there definitely 1 2 will occur in 72. Same way 120, here it is 2 raised to 3, so definitely 1 2 will definitely come as a prime factor for 120. Hence we are writing 2 raised to 1 here, and observe 3 raised to 1 is present in 6 as well as in 72. Here we have 3 raised to 2, so definitely 3 raised to 1 will be present here, and 1 3 is there in 120 also as a prime factor. So we will be writing HCF of these three numbers 6, 72 and 120. We will be writing all the prime factors and the least exponent which is common in all the three numbers. So here we would observe that we will be having 2 raised to 1 into 3 raised to 1, which is nothing but 2 into 3, whose value will be 6. Now, we will be finding what will be the lowest common multiple. So, while writing down the lowest common multiple of these three numbers, we will make sure that we write down the highest exponent possible for all these three numbers. So, here we could observe that the highest exponent of 2 in 6, 72 and 120 is, for 2, it is 3. The highest exponent is 3. So, we are writing down 2 raised to 3. For 3, the highest exponent in all these three numbers is 2. Therefore, we will be writing 3 raised to 2. Now, for 5, it is 1, right? 5 is occurring only once in all the three numbers. So, 5 is having its highest power as 1. Therefore, we will be writing 2 raised to 3 into 3 raised to 2 into 5 raised to 1, which would be 360. So, we got that highest common factor of these three numbers is 6 and lowest common multiple is 360. So, here we observe that HCF of these three numbers 6, 72 and 120 into LCM of these three numbers 6, 72 and 120 is equal to HCF is 6 and LCM we got it as 360. If we will multiply both of them, we are going to get 2160. Now let's look whether the product of these three numbers is also 2160 or not. If we will find out the product of 6, 72 and 120, we are going to get 51,840. So clearly we observe that the product of HCF and LCM of these three numbers is not equal to the product of these three numbers itself. So at the end we will be writing down HCF of 6, 72 and 120
into LCM of 6, 72 and 120 is not equal to 6 into 72 into 120. So, in general, we can say that for any three positive integers a, b and c, HCF of ABC and LCM of ABC, their product, HCF of ABC into LCM of ABC is not equal to A into B into C.
We are going to solve question 1 of exercise 1.2. The question is, express each number as a product of its prime factors. So every number which will be given over here, we need to prime factorize it. Now first number here is 140. So let's find out the prime factorization of 140. Let's divide 140. Since it is an even number, we can divide it with 2. We are going to get 70 as a quotient. Again, 70 is an even number, so we can divide it with 2 and we are going to get 35 as a quotient. Now, if you will try dividing, we won't be able to divide it with 2, right? Because 35 is an odd number. So, we'll try dividing it with 3. On dividing it with 3 also, we are not going to get remainder as 0. So, therefore, we'll try dividing it with 5. Now, 5 sevens are 35. So, we can write down 7 as a quotient over here. And now, 7 is a prime factor. So, we will be dividing 7 with 7 in order to get 1 as a quotient. So, we will be writing now 140 as a product of its prime factors. So, 140 is equals to, we will write down all the prime factors, 2 into 2 into 5 into 7. Now, this can be further written as 2 raised to 2 into 5 raised to 1 into 7 raised to 1. So, this is the way we have prime factorized 140. It can be written as a product of prime factors as 2 raised to 2 into 5 raised to 1 into 7 raised to 1. Now, let's look at the second subpart. So, the second subpart of this question is, we have to prime factorize 156. Now, let's try dividing 156. Since it is an even number, we can divide it with 2 and we are going to get the quotient as 78. Again, 78 is an even number, so we can divide 78 with 2 in order to get 39 as a quotient. Now, 39 is an odd number, so we will try dividing 39 now with 3. If you will try dividing 39 with 3, we are going to get 13 as a quotient. Now we came up with a factor here, which is a prime factor, right? 13 is a prime factor. So definitely it will be divisible by only 30. And hence we are going to get 1 as a quotient. Now we will be writing 156 as a product of its prime factors, which would be 156 is equals to 2 into 2 into 3 into 30, which can further be written as, since 2 is occurring twice, we will be writing 2 raised to 2 into 3 is occurring once, so 3 raised to 1, and 13 is also occurring once, so we will be writing 13 raised to 1. So this will be the product of the prime factors of 156. 2 raised to 2 into 3 raised to 1 into 13 raised to 1. Now let's solve the third subpart of question number 1. So let's divide 3825. Since it is an odd number, we can divide it with 3 first of all, because the sum of all the digits of 3825, it will give us a number which is divisible by 3. So we can divide this number with 3. Therefore, we are going to get 1275 as a quotient. Now, we will be dividing this entire number 1275 again with 3 in order to get 425 as a quotient. Now, this 425, it is not divisible by 3. The reason being, you will get 4 plus 2, 6, 6 plus 5, 11. 11 is not divisible by 3. So, therefore, we will try dividing 425 with 5 because the unit place of 425 is 5. Hence, it is divisible by 5. So, we will try dividing. We are going to get 85 as a quotient.
Now again 85 is neither divisible by 2 nor it is divisible by 3. So therefore we will try dividing it with 5. We are going to get 17 as a question. Finally 17 is a prime number, so therefore we will divide 17 with 17 only, and hence we are going to get 1. Now let's write down 3825 as a product of its prime factors. We will be getting 3825 is equals to 3 into 3 into 5 into 5 into 17. Now since 3 is occurring twice, 5 is also occurring twice, we can write down this in terms of 3 raised to 2 into 5 raised to 2 into 17 raised to 1. So this is the way we have prime factorized 3825 in the product of its prime factors. Those are 3, 5 and 17. Now this is the fourth subpart of question number 1. We have to prime factorize 5005. So we will be dividing first of all 5005 with 5. We are going to get 1001 as a quotient. Now 1001 is neither divisible by 2 nor 3 nor 5. So we will try dividing it with 7. And hence we are going to get the quotient as 143. Now let's try dividing 143 with 11. We are going to get quotient as 13. And since 13 is a prime factor, so we will be dividing 13 with 13 in order to get 1 as a quotient. So now 5005 can be written as 5005 is equals to 5 into 7 into 11 into 13. Now here every prime factor is occurring once. So we will be writing 5 raised to 1 into 7 raised to 1 into 11 raised to 1 into 13 raised to 1. Now this is the fifth subpart of question number 1. We have to find out the prime factors of 7429. So let's prime factorize it. 7429. We can divide it with 17 and we are going to get the quotient as 437. Now next, the number with which we can divide this 437 is 19. So we'll be getting, on dividing 437 with 19, we'll be getting 23 as a quotient. Now again 23 is a prime number, so we can divide 23 with 23 in order to get 1 as a quotient. So now we can write down 7429 equals to 17 into 19 into 23. And since every prime factor in this prime factorization is occurring only once, so we will be writing it as 17 raised to 1 into 19 raised to 1 into 23 raised to 1.
Question number 2 of exercise 1.2. The question is, find the LCM and HCF of the following pair of integers and verify that LCM into HCF is equals to the product of the two numbers. So let's try to solve the subparts. Now this is the first subpart of question 2. We need to find out the prime factorization of 26 and 91 and find out their lowest common multiple and highest common factor. Let's try dividing 26 first. So if we will divide it with 2, we are going to get 13 as a quotient. Again 13 is a prime factor, so let's divide it with 13. We are going to get 1 as a quotient. Now what about 91? So we can divide 91 with 7. That will give us 13 as a quotient. 13 is again a prime number, so let's divide 13 with 13 in order to get 1 as a quotient. So therefore we can write down 26 as 26 is equals to 2 into 13. Now this can be written as 2 raised to 1 into 13 raised to 1. Again 91, we can write down it as a product of prime factors as 7 into 13. Observe, it can be written as 7 raised to 1 into 13 raised to 1. Now what would be the HCF, highest common factor of these two numbers? So we have to write down
the least exponent possible in both the numbers. So observe, for prime factor 2, if you will see, in 26 we have a prime factor of 2, right? 2 raised to 1. But in 91 we don't have that. So we will be writing 2 raised to 0 because 0 is the least exponent possible. Similarly, 7 is appearing in 91 as a prime factor, whereas in 26 we don't have 7 as a prime factor. Therefore, we will be writing 7 raised to 0 over here. And since 13 is occurring in both of them once, therefore we will be writing 13 raised to 1. And hence our HCF here would be 2 raised to 0 into 7 raised to 0 into 13 raised to 1, which is equals to 30. Because anything raised to 0, any positive number or negative number raised to 0 will be giving us 1 as its value. So therefore 2 raised to 0 will be 1, 7 raised to 0 will be 1, multiplied with 13 raised to 1 will give us the entire highest common factor as 30. Now let's find out the lowest common multiple over here. So for lowest common multiple, we will be writing the highest exponent possible. So observe, in 26 and 91, 2 is occurring once in 26, right? So highest exponent possible for 2 would be 1. Similarly, in 91, 7 is occurring once. So we will be writing 7 raised to 1 here. For 26 and 91, 13 is occurring once in both of them. So we will be writing 13 raised to 1. And hence our LCM will be equals to 2 raised to 1 into 7 raised to 1 into 13 raised to 1. The product of all these three numbers will give us 182 as the lowest common multiple. Now we will be finding out the product of these two numbers. 26 into 91 will give us 2366. And the product of HCF and LCM is equals to 13 into 182, which will be again 2366. So what did we conclude? We have verified that product of the two numbers is equals to HCF into LCM. So with this, we are able to verify that the product of two numbers is equals to the product of their LCM and HCF. Now this is the second subpart of question number 2. Here, let's prime factorize 510 first. So we will be getting, on dividing this number with 2, we will get 255 as a quotient. And now we can divide it with 3 because the sum of 255, 2 plus 5 plus 5 will give us a number which is divisible by 3. 2 plus 5 is 7, 7 plus 5, you are going to get 12, right? 12 is divisible by 3. So therefore, this entire number 255 is divisible by 3. Now, if we will divide it with 3, we are going to get 85 as a quotient. And now this 85 is neither divisible by 2 nor 3. So we will divide it with 5. Since the unit place of this 85 is 5, therefore it is divisible by 5. If we will divide it, we will get 17 as a quotient. Now 17 is again a prime factor, so we can divide it with 17. We are going to get 1 as a quotient. So we have done the prime factorization of 510. Let's try dividing 92 now. Let's try to do the prime factorization of 92. So since 92 is an even number, we can divide it with 2. Therefore, we are going to get 46 as a quotient. And again 46 is an even number, we can divide it with 2. We are going to get 23 as a quotient. Now 23 is a prime number itself. So therefore, we are going to divide it with 23 only and we are going to write down 1 as a quotient. And now we will be writing down 510 as 2 into 3 into 5 into 17. So we can observe that every factor here is occurring once. So we will be writing 2 raised to 1 into 3 raised to 1 into 5 raised to 1 into 17 raised to 1. Now let's write down 92 as a product of the prime factors. We will be writing 92 equals to 2 into 2 into 23, which can be written as 2 raised to 2 into 23 raised to 1. Now for finding out highest common factor, we will be writing the least exponent possible in both the numbers for that prime factor. Here in 510 we can see 2 raised to 1, in 92 we can see 2 raised to 2. Therefore, the least exponent possible would be 2 raised to 1. Similarly, for 3 is occurring as a prime factor in 510 but not in 92. So, therefore, the least exponent for 3 would be 0. We will be writing 3 raised to 0. Same happens for 5. 5 is occurring in 510 but not in 92. So, therefore, we will be writing 5 raised to 0. And same applies for 17 also. 17 is occurring as a prime factor in the prime factorization of 510 but not in 92. So, therefore, the least exponent possible for 17 would be 0 and hence we will be writing 17 raised to 0. Same happens for 23. 23 is occurring in 92 as a prime factor but not in 510. We cannot see the prime in the prime factorization of 510. We cannot see 23 at all. So, therefore, the least exponent possible for 23 will also be 0 and hence we will be writing 23 raised to 0. Now, if we will try to multiply all these values 2 raised to 1 into 3 raised to 0 into 5 raised to 0 into 17 raised to 0 into 23 raised to 0, these all values 3 raised to 0 into 5 raised to 0 into 17 raised to 0 into 23 raised to 0 will give us 1 and multiplying it with 2 raised to 1 will lead us to 2. Now, let's talk about what is LCM of these two numbers. So, for LCM, we will be writing the highest exponent possible in the prime factorization of both the numbers. So, here we could see that for 2, the highest exponent possible in 510 it is 1 and in 92 it is 2. So, therefore, we will be taking the highest exponent, that is 2. And for 3, it is occurring in 510 but not in 92. So, therefore, the highest exponent possible would be 1. Now, let's write down lowest common multiple. So, for lowest common multiple, we will be looking at the highest exponent possible. So, if you will look carefully, for 2, it is occurring twice in 92 but once in 510. So, therefore, the highest exponent possible is 2 and hence we will be writing 2 raised to 2 here. Now, for 3 is occurring once in 510 but not in 92. Therefore, we will be writing the exponent, the highest exponent of 3 as 1 and hence it will be written as 3 raised to 1. For 5 also, we will be writing 5 raised to 1. It is coming as a prime factor in 510 but not in 92. So, therefore, we will be writing 5 raised to 1. For 17 again, we will be writing 17 raised to 1 as it is occurring once in the prime factorization of 510 but not in 92. Same happens for 23. It is occurring as a prime factor in 92 but not in 510. So, therefore, we will be writing 23 raised to 1. So, what did we conclude? While writing down the HCF, we look for the lowest exponent, right? Least exponent. But while writing down the lowest common multiple, we look for the highest exponent possible for both the numbers. Now, if you will try to multiply all these numbers, we are going to get 2 raised to 2 into 3 raised to 1 into 5 raised to 1 into 17 raised to 1 into 23 raised to 1. So, this entire product will give us 23,460 as the lowest common multiple. Now, the product of the two numbers is equals to 510 multiplied with 92, which is equals to 46,920. And the product of their HCF and LCM is equals to 2 into 23,460, which will give us 46,920. So, what did we observe? We got the same value in the product of the two numbers as well as the product of their HCF and LCM. So, what did we observe? We got the same value while doing the product of the two numbers and the product of their HCF and LCM. So, we will be writing finally that we have verified product of the two numbers is equals to the product of their highest common factor and lowest common multiple. Now, this is the third subpart of question number 2. Here, we have to find out First of all, the prime factorization of 336. We have to divide it with 2 since it is an even number. So now we are going to get quotient as 168. And if you will divide it again with 2, since 168 is also an even number, if you will divide 168 with 2, we are going to get 84 as a quotient. Again 84 is an even number, so we can divide it with 2 in order to get 42 as a quotient. Now let's try dividing 42 with 2 since it is an even number, so we are going to get 21 as the quotient. Now 21 is an odd number, so now we will be dividing it with 3. Since the sum of 2 plus 1 is equals to 3 and 3 is divisible by 3. So we will be dividing 21 with 3 in order to get 7 as a quotient. And now 7 is a prime factor, so we can divide 7 with 7 in order to get 1 as a quotient. Now we are left with 54. So let's prime factorize 54 also. If we will divide 54 with 2, we are going to get 27 as a quotient. Now since here 54 is an even number, we first of all tried dividing it with 2. Now 27 is an odd number, so we can divide it with 3 because the sum of 2 and 7 will give us 9 and 9 is divisible by 3. So therefore we will divide 27 with 3 in order to get 9 as a quotient, and hence we can divide 9 with 3 in order to get 3 as a quotient. Finally, we will be dividing 3 with 3 in order to get 1 as a quotient. So therefore, now we will be writing 336 and 54 as the product of their prime factors. 336 is equals to 2 into 2 into 2 into 2 into 3 into 7, which can be written as 2 raised to 4 into 3 raised to 1 into 7 raised to 1. Also 54, we can write it down as 2 into 3 into 3 into 3. And here this can be written as 2 raised to 1 into 3 raised to 3. Now for HCF, highest common factor, we will be writing down the smallest exponent possible in both the numbers for that particular prime factor. So if you will observe, 2 is occurring 4 times in 336, whereas in 54 it is occurring only once. So therefore we will be writing 2 raised to 1 here. Same for 3, it is occurring once in 336 but thrice in 54. So therefore we will be writing 3 raised to 1. Now in 336, 7 is occurring once but not at all in 54. So therefore we will be writing 7 raised to 0 here. If we will multiply 2 raised to 1 into 3 raised to 1 into 7 raised to 0, we are going to get 2 into 3, which is 6. And now we will be finding out the lowest common multiple. So for lowest common multiple, we will be looking at the highest exponent possible, right? Now here for 336, the highest exponent of 2 is 4, right? Here it is 1 and over here you can see it is 4. So therefore we will be writing for 2 raised to 4. The exponent we will be writing it as 4. Now for 3, what about for 3? Here it is occurring once, 3 raised to 1, whereas here it is occurring thrice. So we will be writing 3 raised to 3 over here. Now for 7, it is occurring once here in 336 and not at all in 54. So therefore we will be writing 7 raised to 1. Now if we will multiply all these values, 2 raised to 4 will give us 16, 3 raised to 3 will give us 27 and 7 raised to 1 will give us 7. So if we will multiply all these values together, we are going to get 3024 as the product. Now if you will find out the product of the two numbers, that is 336 with 54, we are going to get the product as 18,144. Now let's check whether the product of the HCF and LCM is it the same or not. So if you will multiply highest common factor with lowest common multiple of these two numbers, we are going to get 6 into 3024, which would be 18,144. Now here we observe that we are getting a same number, right? If you will multiply the two numbers 336 with 54, we are going to get the same number as we are multiplying the product of their HCF and LCM. And hence we can write down the product of the two numbers is equals to their highest common factor into their lowest common multiple. Question number 3 of exercise 1.2. So the question is,
Find the LCM and HCF of the following integers by applying the prime factorization method. So remember, here we have to apply only prime factorization method in order to find out the lowest common multiple and highest common factor of the following integers. So the first subpart here is 12, 15 and 21. Let's prime factorize. For 12, we are going to get 2 6 are 12. Now 2 3s are 6. For 3, we will divide it with 3 only. So we are going to get 1. So we can write down 12 as 2 into 2 into 3, which can be written further as 2 raised to 2 into 3 raised to 1. Now since 15 is an odd number, we will be dividing 15 not with 2. We will start division of 15 with 3. So we are going to get 5 as a quotient. Now 5 is a prime factor, so we will be dividing 5 with 5 in order to get 1. Let's write down 15 as the product of the prime factors. 15 will be equals to 3 into 5, which can be written as 3 raised to 1 into 5 raised to 1. Now let's do the prime factorization of 21. We are going to get 21 when divided with 3 will give you 7 as a quotient, and 7 is a prime factor, so we will divide it with 7. We are going to get 1 as a quotient. Therefore, we will be writing 21 as 21 equals to 3 into 7, which can be written as 3 raised to 1 into 7 raised to 1. For highest common factor, we will be writing down the least exponent possible for that prime factor. So here observe, in 12, 15 and 21, the least exponent of 2 is 0. It is not occurring in 15 or 21. So therefore, we will be writing 2 raised to 0 here. 3 is occurring once in all the 3 numbers, 12, 15 and 21. We can observe 3 raised to 1 here, 3 raised to 1 here, 3 raised to 1. So we will be writing 3 raised to 1. Now, since 5 is not coming as a prime factor in 12 and 21, we will be writing 5 raised to 0. And also 7 is not coming as a prime factor in 12 and 21, so we will be writing 7 raised to 0. The least exponent possible is 0. Now, if we will multiply all these numbers, we are going to get 3 as its value. Since 2 raised to 0, 5 raised to 0 and 7 raised to 0, their value will be 1. So, on multiplying 1 with 3 raised to 1, we are going to get 3. Now, let's find out the LCM, lowest common multiple of 12, 15 and 21 using prime factorization method only. 12, 15 and 21. First of all, we will divide it with 2. So, we are going to get 6 over here, here 15 and here 21. Now again, we can divide it with 2. We are going to get 3 over here, here 15 and here 21. Now, we can divide these all 3 numbers with 3. We are going to get 1 here, 5 here and 7 here. Now, we will try to divide all these 3 numbers with 5. So, here we are going to get only 1. Here, we are going to get 1 as a quotient, and for 7, we will keep it as it is. If you will divide 7 with 7, we are going to get finally, for all the 3 numbers, we are going to get the quotient as 1 only. So, this is the way we can do the prime factorization and find out the LCM, lowest common multiple of 3 numbers. We will be writing lowest common multiple is equals to, LCM is equals to 2 raised to 2 into 3 raised to 1 into 5 raised to 1 into 7 raised to 1. So you can observe 2 is occurring twice, 3 is occurring once, 5 is occurring once, 7 is occurring once. So the product of all these numbers will give you 420. Now this is the second subpart of question 3. Let's try dividing 17 first of all. 17 is a prime factor, so we will get 1 as a quotient on dividing 17 with 17. Again, for 23, since it is a prime number, so we will divide 23 with 23 in order to get 1 as a quotient. Again, let's divide 29. Let's prime factorize 29. So we are going to get, on division of 29 with 29, since it is a prime number, we are going to get
1 as a quotient. So therefore we can write down 17 equals to 1 into 17, and hence it can be written as 17 raised to 1. 23 can be written as 1 into 23, which will be written as 23 raised to 1. And 29 can be written as 1 into 29, which can be written as 29 raised to 1. So the highest common factor possible would be 17 raised to 0 into 23 raised to 0 into 29 raised to 0, which will be equals to 1. Now for lowest common multiple, let's use prime factorization method. So what we are going to do, we'll be writing 17, 23 and 29 and try dividing it with first of all 17. So here we are going to get 1, here 23, here 29. Now again, if we will divide it with 23, we are going to get 1 here and 29 over here. Finally, we will be dividing it with 29. So on dividing it with 29, we are going to get 1, 1 and 1 over here as well. So finally, we will be writing LCM, lowest common multiple, as LCM is equals to 17 raised to 1 into 23 raised to 1 into 29 raised to 1. The product of all these three numbers, 17, 23 and 29, will give us 11,339. Now this is the third sub part of question 3. Here we have to find out LCM and HCF by using prime factorization method. So first of all, we will prime factorize 8. If you will divide 8 with 2, we are going to get 4 as a quotient. And on dividing 4 with 2, we are going to get 2 as a quotient. Again, on dividing 2 with 2, we are going to get 1 as a quotient. Now, for 9, since it is an odd number and it is divisible by 3, we can divide 9 with 3. We are going to get 3 as a quotient. And on dividing 3 with 3, we are going to get 1 here. Now, for 25, we can divide it with 5. Since the unit place of this 25 is 5, so it is divisible by 5. We are going to get 5 as a quotient. Again, 5 is a prime factor, so we will divide it with 5 in order to get 1 as a quotient. Therefore, we will be writing 8 is equals to 2 into 2 into 2, 2 raised to 3. 9 is equals to 3 into 3, 3 raised to 2. And 25 is equals to 5 into 5, 5 raised to 2. So finally, the highest common factor of all these three numbers will be equal to 2 raised to 0 into 3 raised to 0 into 5 raised to 0, which is equals to 1. Here we could observe that the least exponent possible for 2, 3 and 5 is 0. Therefore, we are writing 2 raised to 0 into 3 raised to 0 into 5 raised to 0, which is equals to 1. Now let's find out the lowest common multiple using prime factorization method. So we'll be dividing 8, 9 and 25. So if we will try dividing it with 2, we are going to get 4, over here 9 and over here 25. Again, on division with 2, we will get 2 here, 9 here and 25 here. Again, on dividing it with 2, we are going to get 1 here, 9 here and 25. Now, we will be dividing it with 3. So, we are going to get 1 here, 3 here and 25 here. Again, on division with 3, we are going to get 1 here and 25 here. If we will divide it with 5, we are going to get 1 here and 5 here. Finally, on dividing it with 5 will give us 1, 1 and 1 over here. So, we will be writing down the LCM as LCM is equals to 2 raised to 3 into 3 raised to 2 into 5 raised to 2. Observe, 2 is occurring thrice, 3 is occurring twice and 5 is also occurring twice. So, therefore, we are writing 2 raised to 3 into 3 raised to 2 into 5 raised to 2, which will be giving us 1800.
Question number 4 of exercise 1.2. In this, it is given that HCF of these two numbers 306 and 657 is equals to 9. HCF is given, those two numbers are given. We have to find out LCM, lowest common multiple of 306 and 657. Let's go through the solution. So as we know here that highest common factor HCF is given to us for these two numbers 306 and 657. Its value is equals to HCF value is equals to 9. And we know this statement that lowest common multiple multiplied with highest common factor is equals to the product of those two numbers. So in order to find out lowest common multiple, what are we going to do? We will divide highest common factor with product of the two numbers. So we will write down 306 into 657 divided by 9. Now the product of 306 and 657 is equals to 2,01,042, and if we will divide it with 9, we are going to get 22,338. So that is going to be our lowest common multiple for these two numbers 306 and 657. Question number 5 of exercise 1.2. In this question, it is said that we have to check whether 6 raised to n can end with the digit 0 for any natural number n, which means if you will write down, let's say 6 raised to 1, 6 raised to 2, 6 raised to 3, for all these powers of n, will it ever end with 0? That we have to check. So we have to find out that for any natural number n over here, is it possible for 6 raised to n to end with digit 0? Let's go through the solution. So we know that if any number ends with the digit 0, then it should be divisible by 10, or we can say it is also divisible by 2 and 5. So for example, we can observe here that 10 is equals to 2 into 5, right? In the prime factorization of 10, we can see that it is divisible by 2 as well as 5. So in the prime factorization of 6, what do we have? If you will try to prime factorize 6, what are we going to observe? Let's divide it with 2. We are going to get 3 as a quotient. Again, if you will divide 3 with 3, we are going to get 1 as a quotient. So what did we observe? That 6 is equals to 2 into 3. So similarly, we can write down in the prime factorization of 6 raised to n, it will be equal to 2 into 3 whole raised to n. So in this prime factorization, we can observe that we don't have 5, right? We have 2, but we don't have 5. So it is clear that 5 is not present in the prime factorization of 6 raised to n. So what we will conclude? That for any natural number n, 6 raised to n will not be divisible by 5, which means that 6 raised to n cannot end with digit 0 for any natural number n. Question number 6 of exercise 1.2. The question is, we have to explain why this entire number 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, these two numbers are composite numbers. So we know, right, what are composite numbers? Composite numbers are those natural numbers which have more than two factors, right? So we have to show here that these two expressions, these two numbers which are given over here, they have more than two factors. That's all we need to show. So let's go through the solution. So we have this expression 7 into 11 into 13 plus 13. Now we can see over here that 13 is a term which we can take common, right? So let's do that. If you will take 13 common, in bracket we will have 7 into 11 over here. And from this 13 we are going to write it down. On taking 13 common, we will have only plus 1 right here. Now 13 into 7 into 11, we know it's 77 plus 1. We will write it down as it is. Now 77 plus 1, its value is 78, and this 13 we are going to multiply with it. So 13 into 78, we are going to get 1014. Now we have to check whether this 1014 is a composite number or not. And for that we are going to do the prime factorization. So from prime factorization, we are going to get the prime factors, right? So these are the prime factors whose product is going to give us 1014. They are 13 into 13 into 2 into 3. So these are all the prime factors whose product will lead us to 1014. Now clearly we can see that since the given expression has more than two factors which are 2, 3 and 13, therefore this entire expression 7 into 11 into 13 plus 13 is definitely a composite number. Because what is the definition of composite number? We know that the composite number is a natural number which has more than two factors, right? And here it is clearly evident that for 1014 it is having more than two factors, that is 2, 3 and 13, right? We have to find out just more than 2, okay? That's it. So with that we can easily say that the number is a composite number. Now we are going to find out whether this entire number is also a composite number or not. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. So here clearly we can see that from this entire expression 7 into 6 into 5 into 4 into 3 into 2 into 1, we have a 5 over here, as well as over here also we have a 5, right? So what are we going to do? Similarly, like the previous one, we will take 5 common. So on taking 5 common, we are going to get in brackets 7 into 6 into 4 into 3 into 2 into 1. And because of this plus 5, if we will take 5 common, we are going to get plus 1 over here. Now, the product of 7, 6, 4, 3, 2 and 1 will give us 1008. And to this 1008, we are going to add 1. So which is going to give us 1009, right? And 5 will multiply as it is, like the previous step. So 5 into 1009, this is the step that we got. Now the multiplication of 5 with 1009 will give us 5045. Now again here we are going to do prime factorization of 5045. So the prime factors that we will obtain, it would be 5 into 1009. Now clearly for this number 5045, if we will do the prime factorization, we are going to get 5 into 1009. Now since the given expression has more than two factors which are 5, 1009 and 5045, so we know that the number itself will also be a factor of that number, right? So definitely we have over here 3 factors, right, which is more than 2. So what can we say? That this entire number 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is definitely, this entire expression is definitely a composite number, right? Because when we tried simplifying it and we got a number, on prime factorization of that number we clearly obtained that it has more than 2 factors. So whenever a number has more than 2 factors, what do we call it? We call it a composite number. So definitely, therefore we can say that this entire expression 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Question number 7 of exercise 1.2. Let's look at the question. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field. So Sonia is taking 18 minutes to complete one round, while Ravi takes 12 minutes for the same, which means Ravi is taking 12 minutes to complete the same round. Suppose they both start at the same point and at the same time and go in the same direction. So these 3 things are important. They are starting at the same point, at the same time, as well as in the same direction they are going. So we have to find out that after how many minutes will they meet again at the starting point. So clearly, what did we see here? If let's say Sonia is starting and she is taking 18 minutes to complete a round like this. So Ravi is taking lesser time to complete the same round. Let's say Sonia is taking here 18 minutes. So Ravi will take lesser time to complete the same round. Okay, 12 minutes he is taking. So we have to find out that if they are starting at the same point, at the same time, and if they both are going in the same direction, let's say they both are going in this direction. So we have to find out after how many minutes will they meet again. So which means we have to find out a multiple of 18 and 12, right? But here, the multiple that we will be finding out, it has to be lowest multiple. So lowest common multiple we have to find out in order to say after how many minutes will Sonia and Ravi, both of them, meet again at the starting point. Let's go through the solution. So clearly we saw that Ravi is taking lesser time, right, than Sonia for completing one round of that circular path. Now the time taken by Ravi was 12 minutes. So we can write down time taken by Ravi is equals to 12 minutes. Whereas the time taken by Sonia is equals to 18 minutes. Now the total time required to meet again at the starting point when they both start at the same time and in the same direction, it will be the lowest common multiple of 12 and 18. Because there are many multiples possible, right, for 12 and 18. But we need to find out that after how many minutes they meet again at the starting point, but that has to be the lowest common multiple, right? We want them to meet as soon as possible, right? So therefore we have to find out the lowest common multiple of 12 and 18. So we will do the prime factorization of 12. Let's see what we get. 12, if we will divide it with 2, we are going to get 6 here. Let's divide 6 with 2 again. We are going to get 3 as a quotient. So on dividing with 3, we are going to get 1. So we can write down 12 equals to 2 into 2 into 3. Now we will see what about 18. So we will prime factorize 18 also. 18 on dividing with 2, we are going to get 9. Again, 9 is not divisible by 2. So we will divide 9 with 3 and we are going to get 3 as a quotient. Again, dividing 3 with 3 will give us 1. So we can write down 18 is equals to 2 into 3 into 3. Now, remember we have to find out the lowest common multiple. So how are we going to proceed? Lowest common multiple of 12 and 18, we have to take the highest exponent possible for the prime factor in both the numbers. So here we can write down 12 as 2 into 2 into 3. So that can be written as 2 raised to 2 into 3 raised to 1. 2 raised to 2 into 3 raised to 1. Now, how can we write down 18 as? So it can be written as 2 raised to 1 into 3 raised to 2. Now look, for 12, the prime factor 2 is having the exponent as 2 over here. Whereas in 18, the prime factor 2 is having 1 as its exponent. Among both of them, what is the highest? 2, right? The exponent 2 is highest. So we will write down 2 raised to 2. Similarly, let's look for 3. So for 3 prime factor, we can see in 18 it is having exponent as 2, 3 raised to 2, right? And in 12, we are having the exponent of 3 as 1. So among both of them, what is the highest one? Definitely 2, right? So we will write down 3 raised to 2. Now we will multiply these two in order to get the lowest common multiple. So 2 raised to 2, which will be 4, into 3 raised to 2, which will be 9. So 4 9s are 36. This is what we got as the lowest common multiple of 12 and 18. So therefore we can say that after 36 minutes, Ravi and Sonia, they both will meet again at the starting point.
Theorem 1.3. Let P be a prime number. So let's say we are assuming P as a prime number. P value is 3. Okay, this is our assumption. If P divides A square, then P divides A, where A is a positive integer. So let's say that A, which is a positive integer, we are taking its value as 6. Now definitely if A is 6, A square will be equals to 6 square. 6 into 6, which is 36. So according to this theorem, what we understood is that if 3 is dividing if 3 divides a square, which is 36, then 3 will divide 6 also. So the same way you can understand that if 2 divides 36, then 2 will divide 6 also. So this theorem is nothing but the application of fundamental theorem of arithmetic. In this, what are we understanding is that if you have a prime number, let's say that is 3, and if it is dividing the square of a number 36, if you are dividing 36 with 3, you will have no remainder, right? So if 3 divides 36, then 3 will divide the square root of 36 also, which is 6. So 3 will divide 6 also. Same happens in this example also. You can observe if 2 divides 36, then you can say 2 divides 6 also. Now, using this, we are going to prove the next theorem, which is Theorem 1.4. It says that we have to prove here that root 2 is irrational. Now, in order to prove this theorem, we are going to use method of contradiction. Method of contradiction. What is the meaning of this method? That it implies that we are going to assume something first of all wrong. Okay? And based on that wrong assumption, you will get the result also wrong. So we will conclude that our result is wrong because our assumption was incorrect. So this is the way we have to prove Theorem 1.4. Here, let's assume first of all root 2 be a rational number. Be a rational number. So we have to prove over here that root 2 is irrational, right? We are starting with a wrong assumption that let root 2 be a rational number. So it means that if root 2 is a rational number, you can write down root 2 in the form of p upon q, right? Where q is not equal to 0. Along with that, p and q, they are co-primes. Co-primes. Now, what is the meaning of co-primes? It basically means that the HCF, the highest common factor of P and Q, will be equal to 1. You can write it down like that is HCF of P and Q is equals to 1. So, if root 2 is a rational number and it can be written in the form of P by Q, where Q is not equals to 0, therefore here P and Q are co-primes, and the HCF of P and Q will be equals to 1. So, if we will try to cross multiply this Q, we will multiply it with root 2. We are going to get root 2Q equals to P. Now, in the next step, we will square both the sides. So, on squaring, both sides, we'll get root 2q whole square, which would be equals to 2q square, and square of p will give us p square. So, according to this, what can we convey? That we can write it down in the form of q square is equals to p square upon 2, which means that here 2 divides p square. Now, according to our previous theorem, if 2 divides p square, we can conclude that it will imply 2 divides p also, right? If 2 divides p square, then according to the previous theorem, Theorem 1.3, we can write down 2 divides p also. Now, here we will write down let p by 2 equals to c. Let p by 2 equals to c. So, according to this, p will be equals to twice of c, right? P will be equals to twice of c. Now, this value of P, we are going to substitute it in this equation. Let's number this equation as equation number 1. So, we will write down, put value of P equals to 2c in equation 1. We can write it down, root 2q equals to, in place of P, we will write down 2c. Now again, after this step, we are going to square both the sides. So on squaring both the sides, we will get 2q square equals to 4c square. And hence, we can simplify it further, which can be written as q square equals to 4c square upon 2, which can be written as 2c square. So we got q square equals to 2c square. Q square equals to 2c square. Therefore, we can write it down in the form of q square by 2 is equals to c square. Now with this, what did we understand? That definitely here 2 divides q square. And if 2 is dividing q square, then it will imply that 2 divides q also. So here we are going to write down q by 2 equals to, let's say, some number d. Let q by 2 equals to d, which implies it can be written as q equals to twice of d. Now here in the previous case, we assumed p equals to 2c and we got q equals to 2d, which means you can observe in both of them 2 is a common factor, right? P and q, both of them are having 2 as a common factor. But according to the definition of rational numbers, what did we wrote it over there? That if root 2 is equals to p by q, then p and q should be co-primes, right? They should not have any other common factor apart from 1. But here, as a result, we got that p and q are having 2 as a common factor, which implies that we can write down p and q cannot have as a common factor because according to our assumption, p and q are co-primes, right? Which means HCF of p and q should be equals to 1. It should not be equals to any other number. Now here there is a contradiction, right? We assumed something and as a result we got something else. We got p and q have 2 as a common factor, but we assumed in the initial part, we assumed that p and q are co-primes. Now this contradiction has arisen because of our wrong assumption. Because initially we assumed wrong thing. Therefore, we will write down this contradiction has arisen because of our wrong assumption. That root 2 is rational number. So, if this statement root 2 is rational number, if this assumption is wrong, then what is the correct statement? Definitely it will imply that root 2 is irrational number. Right? If root 2 is not a rational number, then what is the other way around? Definitely root 2 is a rational number. So this is called as method of contradiction. We assume something incorrect, and based on that, the result we are going to get as wrong, right? So we conclude that the contradiction has arisen because our initial assumption was incorrect, and hence we conclude that definitely root 2 is a rational number over here. The decimal expansion of rational numbers and irrational numbers. So first of all, look at this classification. We know real numbers can be classified into two categories, that is with decimal, the numbers which are having decimal expansions, and without decimal, the number without decimal expansions. Right? Such numbers are called as integers. The examples of that include, -3, -2, 0, 1, 2, 3, so on. Right? These are all the integers. Now, in case if they are having decimal expansion, in that case, it can be further classified into two categories. Where first category is the decimal expansion is terminating. The decimal expansion is terminating. Now, what happens over here? The decimal expansion will terminate after a certain point of time. The examples of that would be 0.5. Right? It is terminating after one decimal expansion. So 0.5, then 1.25. These are some of the examples of terminating decimal expansion. Now the other category is non-terminating. Now in non-terminating also we have two subcategories. That the decimal expansion is non-terminating as well as repeating. So we can say the decimal expansion is non-terminating as well as there is some pattern that it is repeating. The examples of that will be, let's say you have 1.23, 23, 23 and so on. These three dots includes that it will not terminate. Right? These three dots means that it will not terminate. So here you can see that 2, 3 is a pattern. It keeps on repeating, right? In this decimal expansion. Same way you can consider 0.545, 545. So this 545, 545 it keeps on repeating, right? So we can consider this decimal expansion as non-terminating and repeating. Now the other classification under non-terminating is non-terminating as well as non-repeating, which means the decimal expansion will neither terminate nor repeat. So we can write it down in the form of, let's say you have 1.234567 and so on. Okay, so in this decimal expansion you can say that it is not terminating, right? It is not terminating after a certain point of time, as well as it is not repeating also. Same way you can consider another example as 0.785769. So here also you can see that there is no pattern over here, right? So 785, 769, there is nothing such as which is repeating. There is no pattern over here which keeps on repeating. So therefore it is called as non-terminating, non-repeating. Now these two categories, terminating decimal expansion and non-terminating repeating decimal expansion, they fall under rational numbers. They fall under rational numbers, which basically means that these numbers can be written in the form of p by q, where q is not equals to 0. Now, what about non-terminating, non-repeating decimal expansions? Then such numbers are actually irrational numbers. Such numbers are actually irrational numbers, which means you cannot write it down in the form of p by q. Okay, you cannot write down irrational numbers in the form of p by q. So this was the classification of real numbers based on decimal expansions. With decimal, there are two subcategories, terminating as well as non-terminating. In terminating, there are two subcategories, non-terminating repeating and non-terminating non-repeating. Now, terminating decimal expansions and non-terminating repeating decimal expansions, these two fall under the case of rational numbers. Whereas non-terminating non-repeating decimal expansions, they are nothing but irrational numbers. Now, next we are going to go through some theorems. So, theorem 1.5. Here, let x be a rational number whose decimal expansion terminates. So, we will consider, let's say, x is equals to 0.5. The decimal expansion is terminating, right? Then, x can be written in the form of p by q. They are saying that if it is terminating, if x is terminating, then you can write down this 0.5 in the form of p by q, where p and q are co-primes, which means the HCF of highest common factor of p and q will be 1, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So let's write out. We can write down 0.5 into 10, and in the denominator also we can multiply 10, right? So what are we going to get? We will get 5 by 10. Now, is this simplified? No, we can simplify it further in the form of 1 by 2, right? So here you can see the denominator is 2, right? Which can be written in the form of 2 raised to n and 5 raised to m. You can write it down it in the form of 1 upon 2 raised to 1 into 5 raised to 0. So this is what this theorem 1.5 is. That if you have a decimal expansion which is terminating, then that number can be written in the form of p by q, where p and q are co-prime. You can observe in 1 by 2, 1 and 2 are co-prime because they are not having any other common factor apart from 1, right? As well as the denominator q will be of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So, if you will compare 2 raised to 1 into 5 raised to 0 with 2 raised to n into 5 raised to m, you can clearly observe that n value is 1 and m value is 0 over here, right? And both of them are non-negative integers. So, this is what this theorem means, theorem 1.5. Next, we have theorem 1.6. Here, this theorem says that let x equals to p by q be a rational number. So, let's say x is equals to 1 upon 5. Okay, this is a rational number. So, they are saying that such that prime factorization of q is of the form 2 raised to n into 5 raised to m. Now, the prime factorization of q is what? 5, right? We can write down 5 in the form of 2 raised to 0 into 5 raised to 1, right? Now, if this happens, then this theorem conveys that x has a decimal expansion which will terminate. So, it means that here x will have a decimal expansion which will terminate. Now, we can try it out also. What we can do, in order to find out the decimal expansion without division, what we can do is, we can multiply the numerator and denominator with the same power as 5 is having. So, here we will multiply numerator and denominator with 2. What are we going to get? We will get 2 in the numerator, and in the denominator we will be having 2 raised to 1 into 5 raised to 1. So 2 into 5 we will get 10, right? So this can be easily written as 2 upon 10. Now we know we can easily find out the decimal expansion of this number. It is 0.2. So what did we observe? That here x was equals to 1 by 5, right? It is in the form of a rational number p by q, where the prime factorization of q is in the form of 2 raised to n and 5 raised to m, where n and m are non-negative integers. Then in that case we observed that the decimal expansion of this number terminates. So now we are at theorem 1.7. Here you can observe that let x equals to p by q. Let x equals to p by q, where p and q are co-primes, which means the highest common factor of p and q will be equals to 1. Be a rational number. We are assuming x to be a rational number which can be written in the form of p by q, where p and q are co-primes, such that the prime factorization of q is not of the form, this is very important, it is not of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So what are we assuming? Let's say our example is x is equals to 1 by 3. Now you can clearly see the denominator here q is equals to 3, right? Which is not of the form 2 raised to something and 5 raised to something, right? 2 raised to something into 5 raised to something. This 3 is not of this form, right? The prime factorization of 3 will not be of this form. So what did we understand from this? Then definitely according to this theorem, the decimal expansion of this 1 by 3 will be non-terminating, which means it will not terminate at a certain point of time. It will keep on repeating itself. There will be certain pattern in the decimal expansion which will keep on repeating. So like here you can observe, if you will divide 1 by 3, what are we going to get? We will get 0.3333 and so on, right? These 3 dots indicates that it is not terminating. As well as you can observe that here 3 keeps on repeating, right? 3 is a pattern which keeps on repeating. So therefore this is the meaning of theorem 1.7, that if you have a rational number which can be written in the form of p by q, where p and q are co-primes, and q is not of the form, the prime factorization of q is not of the form 2 raised to something into 5 raised to something, where the exponents of 2 and 5 should be non-negative integers, which means they should be whole numbers. So if you cannot write down the denominator of the rational number in the form of 2 raised to n into 5 raised to m, then that rational number will have a decimal expansion which will be non-terminating and repeating. Repeating is also known as recurring. Exercise 1.3, question number 1. The question is, prove that root 5 is irrational. So again, we will be using over here method of contradiction. Let's start with the solution. So first of all, we will write down let root 5 be a rational number. Root 5 be a rational number. So definitely we can write down root 5 in the form of p by q, and we can write down root 5 equals to p upon q, where q is not equals to 0. Also the conditions are p and q are co-primes, which means the highest common factor, or we can say the HCF of p and q is equals to 1. This is what we have assumed. Now definitely if root 5 can be written in the form of p by q, on cross multiplying we can multiply q with root 5. We'll get root 5q equals to p. Now name it as equation 1. Square on both the sides. So we will squaring, on squaring both sides, we will get root 5q whole square, that will be equals to 5q square, and p whole square, that will give us p square. So from this we can write down q square is equals to p square upon 5. p square upon 5, which implies what? We can say that 5 divides p square. Now if 5 divides p square, 5 is a prime number, if it divides p square, then definitely 5 will divide p also. So we can write down 5 divides p also. Right? Now if this happens, we can assume what? Let's say p by 5 is some number c. Let p by 5, on dividing p with 5, we are going to get some number. Let's say that is c. So from this we can write down, on cross multiplying, p is equals to 5c. Right? Mark it as your equation 2. P equals to 5c, mark it as your equation 2. Now this value of p that you have got, you have to substitute it in equation 1 from equation 2. So we'll write down, put value of p from equation 2 in equation 1. On doing this, what are we going to get? We will get root 5 cube is equals to, in place of p, we will write down 5c. Now again we got root 5 cube equals to 5c. So we will square on both the sides. If you will square on both the sides, it will give us 5q square equals to 25c square. 5c whole square will be 25c square. Now on simplifying this further, what are we going to obtain? We will get q square is equals to 25c square upon 5, which can be written as q square is equals to 5c square. Or we can write down from here, q square upon 5 is equals to c square, which implies 5 divides q square. Now if 5 divides q square, from the theorem we can say that 5 will divide q also. 5 divides q also. Right? Now from this, what did we observe? That let's say if we are dividing q with 5, we are going to get a number, right? A question. Let's say that number is equals to d. So we have assumed let q by 5 is equals to d. And from this we can write down q is equals to 5d. Right? Q equals to 5d. But from the equation 2, we got p equals to, from equation 2, we got p equals to 5c, and here we are getting q equals to 5d. Since q is equals to 5d and p is equals to 5c, what can we say? 5 is a common factor in both of them, p and q. But our assumption said that p and q are co-primes, which means the HCF, the highest common factor of p and q, should be 1. Right? So we will write down, but HCF of p and q was 1 according to our assumption. According to our assumption. So according to our assumption, HCF of p and q was 1, right? But as a result, we got that HCF of p and q came out to be 5. There is a common factor between p and q, that is 5. So this contradiction has arisen due to our wrong assumption. Due to our wrong assumption. Our assumption was that
root 5 is rational. Right? So this contradiction has arisen due to our wrong assumption that root 5 is rational, which basically means that it implies root 5 is irrational. So this is what method of contradiction means. We start with the wrong assumption and as a result we get the result to be wrong, right? So we say that our conclusion is wrong because of our wrong assumption initially. So this is called as method of contradiction. Here we got HCF of P and Q on solving equals to 5. But initially we assumed that HCF of P and Q should be equals to 1 because root 5 can be written in the form of P by Q where P and Q are co-primes, right? The HCF of P and Q should be equals to 1. But as a result on solving we got HCF of P and Q equals to 5. So there is a contradiction in both of them. It has arisen due to our wrong assumption that root 5 is rational. So we will conclude that root 5 is irrational. Question number 2 of exercise 1.3. The question is, prove that 3 plus 2 root 5 is irrational. So let's start with the solution. Over here, again we will follow the method of contradiction. We will assume let 3 plus 2 root 5 be rational number. And if it is a rational number, what can we say? We can write down 3 plus 2 root 5 in the form of P by Q, right? Because a rational number can be expressed in the form of P by Q. Hence, Q should not be equals to 0 over here. Also, the condition is where P and Q are co-primes, which means the highest common factor between P and Q should be equals to 1. HCF of P and Q should be equals to 1. Now, with this, what are we going to start with? We'll write down first of all 3 plus 2 root 5 is equals to P by Q. Now we have 3 on the left hand side. If we will take it towards the right hand side, we will be remaining here with 2 root 5 equals to P upon Q. This plus 3 will become minus 3 over here. Take the LCM now. We can write it down as P minus 3Q upon Q is equals to 2 root 5. Now again 2 is in multiplication over here. So we can take it towards the right hand side. It will get divided. And hence we can write down root 5 equals to P minus 3Q upon 2Q. Now observe very carefully here. Root 5, we know it is irrational number, right? And P minus 3Q upon 2Q, it is rational number. So what can we write down? We will note that root 5 is irrational number. We know that. Right? And the right hand side that we got, it is P minus 3Q upon 2Q, which is rational. We can note here that irrational cannot be equal to rational. Irrational cannot be equal to rational. So left hand side we got it as irrational number and right hand side is rational number. There is a contradiction here. So we can write down this contradiction as arisen due to our wrong assumption. What was our assumption? Our assumption was that 3 plus 2 root 5 is a rational number. So our wrong assumption was that 3 plus 2 root 5
is rational number. Now, if this assumption is wrong, then what is the right thing? Definitely, it implies that right thing would be 3 plus 2 root 5. It implies that is an irrational number. So, this was method of contradiction. What did we observe here? Initially, we assumed 3 plus 2 root 5 as rational number, where it can be expressed in the form of p by q, and HCF of p and q should be equals to 1. After solving it at a certain point of time, we got left hand side as irrational number, which is root 5, and right hand side we got it as rational number, which is p minus 3q upon 2q. Now, left hand side should be equals to right hand side, right? But here, left hand side is irrational and right hand side is rational, which cannot be equal to each other. So, this is a contradiction which has arisen due to our wrong assumption. Our assumption was 3 plus 2 root 5 is rational number, and hence we can conclude that our assumption is wrong. Therefore, 3 plus 2 root 5 is an irrational number.
Question number 3 of exercise 1.3. The question is, prove that the following are irrationals. Over here, the first subpart is 1 upon root 2. So we have to prove that 1 upon root 2 is an irrational number. So we will start first of all with assuming 1 upon root 2 as rational number. So let's write down, let 1 by root 2 be a rational number. So definitely 1 upon root 2 can be written in this form, p by q. Now over here, p as well as q, they both should not be equal to 0. P should not be equals to 0 as well as q should not be equals to 0. Now, why is it so? Because over here we will take the reciprocal. So when we will take the reciprocal, it will become q upon p, right? And on the left hand side, you will get root 2 upon 1. So, which can be written as root 2 is equals to q upon p. So, clearly we can see here that left hand side is root 2, which is an irrational number. Left hand side is irrational. And right hand side is q by p. That's why we have taken p should also not be equals to 0. P is not equal to 0. So therefore here q upon p, which is on right hand side, that is rational. So what did we observe? That left hand side we have an irrational number and on the right hand side we have rational number, right? So here it contradicts, because rational number cannot be equal to irrational. Rational number cannot be equal to irrational. So over here we can see that a contradiction has arisen. So we will write down this contradiction has arisen due to our wrong assumption. That 1 by root 2 is rational. So if this is wrong assumption, then what should be the correct one? The correct statement should be, it implies 1 upon root 2 is irrational. So over here also we have applied the method of contradiction. We assumed first of all that 1 upon root 2 is rational number, and based on that we got left hand side to be irrational and right hand side to be rational number. Now
left hand side has to be equal to right hand side, right? But in this case, in our case, we got left hand side to be irrational number and right hand side to be rational number. So which contradicts, right? Rational number cannot be equal to irrational number, and this contradiction has arisen due to our wrong assumption that 1 upon root 2 is rational number. So which implies that definitely 1 by root 2 is irrational number. Now this is the second subpart of question number 3. So here also we'll assume first of all, let 7 root 5 be a rational number. Which implies that we can write down 7 root 5 in the form of p by q, where q is not equal to 0. Now keep root 5 on the left hand side as it is and take 7 to the right hand side. So we will write down p upon 7q. Now again we are at the same position. Here root 5 is a rational number and p upon 7q is rational number. So what did we get? The left hand side is irrational number and right hand side over here RHS is rational number. Now we know that rational number cannot be equal to irrational number, right? So we will be writing irrational number cannot be equal to rational number. There is a contradiction here. Left hand side is something and right hand side is something else, and this contradiction has arisen due to our wrong assumption. So we will write down this contradiction has arisen due to our wrong assumption. That 7 root 5 is rational number. If this assumption is wrong, what should be the right thing? It implies 7 root 5 is irrational number. Now this is the third subpart of question number 3. 6 plus root 2. Here we have to prove that 6 plus root 2 is irrational. So again we will follow the same procedure. We will write down let 6 plus root 2 be rational number, which implies that we can write it down in the form of 6 plus root 2 is equals to p upon q, where q is not equal to 0. Now again keep root 2 as it is on the left hand side and take 6 on the right hand side. P upon q minus 6. On taking the LCM, we will get p minus 6q upon q, and on the left hand side root 2. So what did we observe here? Definitely root 2 is irrational number. And p minus 6q upon q is a rational number. So left hand side over here is irrational and right hand side is rational number. Now there is a contradiction over here, right? Left hand side is irrational number and right hand side is rational number. So why is this contradiction? Irrational number cannot be equal to rational number. Irrational number cannot be equal to rational number. This contradiction has arisen due to our wrong assumption. That 6 plus root 2 is rational number. So if this assumption is wrong, that 6 plus root 2 is rational number, what is the other way around? Definitely 6 plus root 2 is irrational number. We are going to solve exercise 1.4, question number 1. The question is, without actually performing the long division, we have to state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. So, based on the denominator, we have to categorize whether the decimal expansion will be terminating or non-terminating repeating decimal expansion. All of them are rational numbers, that is already given to us. Only thing that we have to do is we have to tell whether it will be a terminating decimal expansion or a non-terminating repeating decimal expansion. Now the first subpart here is 13 upon 3125. So the first step that we are going to perform here would be, we will do the prime factorization of 3125. So let's start 3125. First of all, let's divide it with 5. We will get 625 as a question. Again, it is divisible by 5. So let's divide it with 5. We will get 125. Again, let's divide it with 5. We will get 25. Again, let's divide it with 5. We will get 5 as a question. And finally, we will again divide it with 5 in order to get 1 as a question. So, definitely, we can write down this 13 upon 3125. The denominator can be written, the prime factorization of the denominator is having 5 into 5 into 5 into 5 into 5. Right? And the numerator is 13. So what can we write it down? We can write it down in the form of 13 upon, since we do not have 2 over here, we can write it down as 2 raised to 0, because 2 raised to 0 will be 1. Multiplied with, we have 5 times, right? So we will write down 5 raised to 5. 5 has been multiplied 5 times. So in the denominator, we have 2 raised to 0 into 5 raised to 5. Now, since over here, denominator is of the form 2 raised to n into 5 raised to m.
since the denominator here is of the form 2 raised to 0 into 5 raised to 5, which is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, or we can say non-negative integers, right? The exponent of 2 is 0, which is a whole number, and the exponent of 5 is 5, which is also a whole number. So therefore, we can write down, therefore, this number 13 upon 3125 will have terminating decimal expansion. This is the second subpart of question number 1. Here we have been given 17 upon 8. So again the same procedure, we will try to prime factorize 8. 8 when divided with 2 will get 4 as a quotient. Again 4 on dividing with 2 will get 2 as a quotient. Again 2 on dividing with 2 will get 1 as a quotient. So we can write down 17 upon 8 as 17 upon 2 into 2 into 2, which can be further written as 17 upon 2 raised to 3 into, since we do not have 5 as a factor here, we can write down the exponent of 5 as 0, because 5 raised to 0 will be ultimately 1. So we will be writing, since denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, therefore 17 upon 8 will have a terminating decimal expansion. Whenever the denominator is of the form 2 raised to n into 5 raised to m, definitely the decimal expansion of that rational number would be terminating decimal expansion. This is the third subpart of question number 1. 64 upon 455. So first of all, we will try to prime factorize 455. On dividing 455 with 5, we are going to get 91 as a quotient. Now, is it possible to divide it with 5? No. So, we will try to divide it with 7. And now we are going to get over here 13. Now, since we know 13 is a prime factor, so therefore it will only be divisible by 13 or 1. So, therefore 13 on dividing with 13, we are going to get 1 as a quotient. Now, we will be writing 64 upon 455 as, we will write down 64 as it is in the numerator, but in the denominator we will write down the prime factorization of 455, that is 5 into 7 into 13. Now clearly you can see that over here we have 5, but we do have 7 and 13 also as a prime factor in the prime factorization of 455. So we will write down, since denominator is not of the form 2 raised to n into 5 raised to m. What does it mean? That in the prime factorization of the denominator 455, we do have other prime factors also, right? 7 and 13. Therefore, the denominator is not of the form 2 raised to n and 5 raised to m, where n and m are whole numbers. Therefore, 64 upon
455 will have non-terminating, repeating, decimal, expansion. So simply only one thing that we have to see over here is whenever we do the prime factorization of the denominator, is the denominator having any other prime factors apart from 2 and 5? In case if it is having any other prime factors apart from 2 and 5, then it will have non-terminating, repeating, decimal, expansion. Now, this is the fourth subpart of question number 1. Here, in the denominator, we have 1600. The question is 15 upon 1600. So, in the denominator, we have over here 1600. Let's do the prime factorization of 1600. We'll get, on dividing it with 2, we'll get 800 as a quotient. Let's divide 800 with 2, we'll get 400 as a quotient. Again, on dividing 400 with 2, we'll get 200 as a quotient. Then dividing 200 with 2, we'll get 100 as a quotient. Now, again dividing 100 with 2, we'll get 50 as a quotient. Dividing 50 with 2 will lead us to 25 as a quotient. Now, 25 on dividing with 5, we will get 5 as a quotient. Finally, 5 on dividing with 5, we will get finally 1. So, therefore, we can write down 1600 in the form of, the prime factorization of 1600 will have 15 upon 2 into 2 into 2 into 2 into 2 into 2. So 2 has been multiplied 6 times, right? And along with that we have twice 5. So we will try to simplify it if possible. We can see that numerator we have 15, right? So the 15 can be written as 3 into 5. And in the denominator we have 2 raised to 6 into 5 raised to 2, which is definitely 5 into 5. So we can cancel out 5 with 5. We are going to get 3 upon 2 raised to 6 into 5 raised to 1. So what did we observe here? The denominator is purely containing 2 and 5 as its prime factors. So definitely here, since denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, we can see it is written in the form of 2 raised to 6 into 5 raised to 1, right? So the prime factorization of 1600, we can observe that on simplifying it, we got, which is definitely of the form 2 raised to n into 5 raised to m, where n is 6 and m is 1, which both of them are whole numbers. So therefore we can say, therefore 15 upon 1600, this rational number will have terminating, decimal, expansion. Now, this is the fifth subpart of question number 1. Here we have 29 upon 343. 29 upon 343. So, let's prime factorize the denominator 343. We can divide it with 7 in order to get 49 as a quotient. Again, dividing 49 with 7 will give us 7 as a quotient. Finally, dividing 7 with 7 will get 1 as a quotient. So, we can write down 29 upon 343. Here, the prime factorization of 343 has 7 into 7 into 7, which means it can be written as 29 upon 7 raised to 3. So, clearly we can observe that in the denominator, the prime factorization of denominator 343 is not having 2 and 5 as its prime factor, right? It is having 7 as its prime factor.
So therefore, whenever you will have any other prime factor apart from 2 and 5, we will say since denominator is not of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, therefore 29 upon 343 will have non-terminating repeating decimal expansion. So only thing here we have to consider is that the denominator should not have any other prime factor apart from 2 and 5 in the prime factorization of denominator, right? So denominator prime factorization should not have any other prime factors apart from 2 and 5. If it is having, then it will definitely have non-terminating repeating decimal expansion. Otherwise, it will have terminating decimal expansion. In case if the prime factorization of denominator is having only 2 and 5 as its prime factors, not any other prime factor, then it will have a terminating decimal expansion. Otherwise, if the prime factorization of denominator is having any other prime factor apart from 2 and 5, so we can consider that the rational number will have, in that case, non-terminating repeating decimal expansion. Now, this is the sixth subpart of question number 1. Here, luckily, in the denominator, we have already been given it in the form of prime factors, right? So, prime factorization has already been done. 23 upon 2 raised to 3, 5 raised to 2. So, clearly we can observe that the denominator, in the prime factorization of denominator, we have only 2 and 5 as its prime factors, right? So, therefore, we will write down since denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers. Therefore, 23 upon 2 raised to 3 into 5 raised to 2 will have terminating decimal expansion, because the denominator is having in its prime factorization only 2 and 5 as its prime factors. Okay, not any other prime factor. So therefore, definitely this rational number will have a terminating decimal expansion. Now, this is the seventh subpart of question number 1. Here clearly we can observe that in the denominator we have 2 raised to 2, 5 raised to 7 and 7 raised to 5. So the denominator is having, apart from 2 and 5, 7 also as the prime factor. Okay, the prime factorization of denominator is having 7 also as a prime factor apart from 2 and 5. So therefore, it is not of the form, since denominator, we will be writing, since denominator is not of the form two raised to n into 5 raised to m. It is having 7 also as a prime factor, right? Where n and m are whole numbers. Therefore, we can definitely say this rational number 129 upon 2 raised to 2 into 5 raised to 7 into 7 raised to 5 will have non-terminating repeating decimal expansion. only condition is that the prime factorization of the denominator should not have any other prime factor apart from 2 and 5. Okay, then we can write down that denominator is not of the form 2 raised to n into 5 raised to m, since 7 is present as a prime factor over here. So therefore this rational number will have non-terminating repeating decimal expansion. Now this is the 8th subpart of question number 1. Now here we can do the simplification. How? We can write down 6 in the form of 2 into 3 and 15 in the form of 3 into 5. In the numerator and denominator we can see 3 is present as a common factor. So we can simplify it and write it down as 2 upon 5. So here this 2 upon 5 can be written as 2 upon 2 raised to 0, because 2 raised to 0 will be ultimately 1, into 5 raised to 1. So clearly, since denominator, here we have denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, we can see the denominator can be written, this 5 can be written in the form of 2 raised to 0 into 5 raised to 1, right? It is not having any other prime factor apart from 2 and 5. So therefore we can say that it is of the form, denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers. Therefore 6 upon 15 will have terminating decimal expansion. Now this is the 9th subpart of question number 1. Here we have 35 upon 50. So is the simplification possible? Let's check it out. 35 upon 50. We can write down 35 as 5 into 7 upon 50 can be written as 5 into 10. So cancel out 5 and 5. You can write it down as 7 upon 10. Now try to do the prime factorization of 10. On dividing 10 with 2, you will get 5 as a quotient. Again on dividing 5 with 5, you will get 1 as a quotient. So therefore we can say 7 upon 10 can be written as 7 upon, the prime factorization of 10 includes 2 into 5. So clearly we can observe that the prime factorization of denominator is of the form 2 raised to 1 into 5 raised to 1. Right? So since we can write down here, since denominator is of the form 2 raised to n into 5 raised to m, where n and m are whole numbers, we can say therefore 35 upon 50 will have terminating decimal expansion, because the prime factorization of 50 has only 2 and 5 as its prime factors, not any other number, right? So therefore it will definitely have 35 upon 50 will definitely have terminating decimal expansion. Now we are at the 10th subpart of question number 1. It is 77 upon 210. So let's try to simplify first of all, if possible. Let's try to simplify 77 upon 210. In the prime factorization of 210, if we will divide 210 with 2, we are going to get 105 as a quotient. Dividing 105 with 3, we'll get 35 as a quotient. On dividing 35 with 5, we'll get 7 as a quotient. And on dividing 7 with 7, we'll get 1 as a quotient. So the prime factorization of 210 is, we can write it down in the denominator, 2 into 3 into 5 into 7. Now clearly 77 can be written in the form of 7 into 11, and in the denominator we have 2 into 3 into 5 into 7. Right? 7 and 7, we have common factor in the numerator and denominator. So at first, if you will look, the prime factorization of 210 is containing 7 and 3 as its prime factors apart from 2 and 5 also. So therefore, you might think that it is not of the form 2 raised to n into 5 raised to n. So that's why the first step is we have to simplify the rational number as much as possible. Let's simplify. We have 7 as a common factor in the numerator and denominator. On simplifying it, we'll get 11 upon 2 into 3 into 5. Still, we have 3 as a prime factor in the prime factorization of the denominator. Right? Apart from 2 and 5, we have 3 also. So therefore, we will write down, since denominator is not of the form two raised to n into 5 raised to m, we can see that apart from 2 and 5, we have 3 also as a prime factor, right? So it is not of the form 2 raised to n into 5 raised to n, where n and m are whole numbers. Therefore, 77 upon 210 will have, this rational number will have non-terminating repeating decimal expansion. So over here, what did we observe? That in the prime factorization of the denominator, we had 3 and 7 as its prime factors apart from 2 and 5 also. So therefore, we tried simplifying it. We were able to cancel out 7 because 7 was common in the numerator and denominator. But still we are left with 3. Apart from 2 and 5, we had 3 as a prime factor also in the prime factorization of denominator. So we wrote, since denominator is not of the form 2 raised to n into 5 raised to m, it is having prime factor other than 2 and 5. So therefore, 77 upon 210 will have non-terminating repeating decimal expansion. Question number 2 of exercise 1.4. The question is, write down the decimal expansion of those rational numbers in question 1 above which have terminating decimal expansions. So we have to take only those subparts which are having terminating decimal expansions, and we have to write down their decimal expansions in this question. Simple. Now, this is the first subpart of question number 2, 13 upon 3125. So, over here, 13 upon 3125, the prime factorization of 3125 is having 5 raised to 5. Now, while writing the decimal expansion without actually dividing this number, what we can do is we have to make sure that the exponent of 5 and 2 should be same number. Okay, so simple. In the denominator we have 5 raised to 5. So what we will do? We will multiply 5 raised to 5 with 2 raised to 5 in the denominator. And this thing cannot be done only in the denominator. We have to do it in the numerator as well. So this is going to give us 13 into 2 raised to 5 is 32. And 2 raised to 5 into 5 raised to 5. It can be written as 2 into 5 whole raised to 5. So simply it can be written as 13 into 32 upon 2 into 5 is 10, 10 raised to 5. Now if you will multiply 13 with 32, you are going to get 460 as a product, and 10 raised to 5 is 1 lakh. Now it is very simple for us to find out the decimal expansion. So what we need to do over here, since we have 5 zeros in the denominator, so therefore we will be shifting the decimal point towards the left hand side 5 times, right? So therefore we will get 61400. We have shifted the decimal point 5 places towards the left hand side, and now here we will put decimal point, and then 0. So 416 divided by 1 lakh will give us 0.00416. So very simple. Only thing that we have to consider over here is, first of all, write down the prime factorization of denominator, then check what is the exponent of 5 and 2 over here. Okay, we have to make sure that their exponents have to be same. We have to take the largest exponent of both of them. So here we can see we have 5 raised to 5, we do not have 2, right? So we will make sure that we will multiply it with 2 raised to 5, and that can only be done if we are doing it in the numerator as well as denominator. So on multiplying 2 raised to 5 with numerator as well as denominator, we got 416 upon 1 lakh, which on dividing will give us 0.00416. So this is the decimal expansion of 13 upon 3125. Now this is the second subpart of question number 2. 17 upon 8. We know we can write down 17 upon 8 as 17 upon 8 can be written as 2 raised to 3. Now observe, the exponent of 2 is 3 here, right? So we have to make sure that we will multiply the numerator and denominator with 5 raised to 3. We have to equate the powers of 2 and 5. Okay, so here since 2 is having the exponent as 3, we are multiplying in the numerator and denominator 5 raised to 3. Now this can be written as 17 into 5 raised to 3 is 125 divided by 2 raised to 3 into 5 raised to 3 can be written as 2 into 5 whole raised to 3. Now 17 into 125 is 2125, and 2 into 5 whole raised to 3 can be written as 10 raised to 3. 10 raised to 3 means 10 into 10 into 10. So that is basically 2125 divided by 10 raised to 3 is 1000. So very simple. The decimal point is after 5. Okay, so we will shift it towards the left hand side for 3 places. So that would be 2.125. You can see that after decimal point we have 3 places over here, because in the denominator we have 3 zeros. That's how we have to find out the decimal expansion without actually dividing 17 by 8. The answer would be 2.125. This is the fourth subpart of question number 2. 15 upon 1600. So we can write down 15 upon the prime factorization of 1600 will have 2 raised to 6 into 5 raised to 2, and in the numerator we have 15. Now observe very carefully, we have 2 raised to 6 into 5 raised to 2. Among them the largest exponent is of 2, right? It is 6. So therefore we will make sure that we will make exponent of 5 also as 6. How can we make that? Only if we will multiply it with 5 raised to 4. So 2 raised to 6 into 5 raised to 2, we have to multiply it with 5 raised to 4. Now that cannot be done only in the denominator. We have to do the same in the numerator as well. So this will give us 15 into 5 raised to 4 is 625. And here we can see 2 raised to 6 into 5 raised to 2 into 5 raised to 4. Bases are same, exponents are different. So we will do what? We will add the exponents. 5 raised to 2 plus 4. Which is going to give us 15 into 625 will be equal to 9375. And in the denominator we will have 2 raised to 6 into 5 raised to 6. Now 9375 divided by, we can write down 2 raised to 6 into 5 raised to 6 as 2 into 5 whole raised to 6, which is basically 9375 divided by 2 into 5 is 10, so 10 raised to 6, which will give us 9375 divided by, we will have 1 and then 6 zeros. So it is basically 10 lakhs, right? Now, what we need to do here, after this point of time, we can see that there are 6 zeros in the denominator. So we will be trying to shift the decimal point, which is just after 5. We will shift it towards the left 6 times. So therefore, we will get 5, 7, 3, 9 and then 0, 0. We have 6 numbers right over here. After that, we will put a decimal point and then we will write down 0. So 0.009375 will be the decimal expansion of 15 upon 1600. Now this is the 6th subpart of question number 2. Here we have 23 upon 2 raised to 3 into 5 raised to 2. We can see among 2 and 5, the largest exponent is of 2, which is 3, right? So we will try to make them equal by multiplying 23 with 5 raised to 1 and denominator also with 5 raised to 1. Because if we are multiplying something, we cannot do it only to the denominator. We have to do it to the numerator as well, right? So now 23 into 5, that is 115. And in the denominator, we will be having 2 raised to 3 into 5 raised to 2 into 5 raised to 1. That is 5 raised to 2 plus 1. If the bases are same, the exponents will get added on multiplying, right? Now, here we will have 115 divided by 2 raised to 3 into 5 raised to 2 plus 1 is 5 raised to 3. So, which can be written as 115 divided by 2 into 5 whole raised to 3. Now, 2 into 5 is 10. So, 10 raised to 3. 10 raised to 3 is 1000. So, we can write down 115 upon 1000. Now, what we will do? Since we have 3 zeros in the denominator, therefore, we will try to shift the decimal point, which is after 5, towards 3 places towards the left side. So, therefore, we will be doing it as 0.115. This will be the decimal expansion of 23 upon 2 raised to 3 into 5 raised to. So, only trick is we have to look at what is the highest exponent among 2 and 5. Whichever is the highest, we will try to make the other one also having the same exponent. Okay, so here you can observe that 2 raised to 3. 2 is having 3 as its exponent and 5 is having 2 as its exponent, among which 3 is the highest one, right? So we will try to make the exponent of 5 also as 3 by multiplying in the numerator and denominator 5. Now, this is the 8th subpart of question number 2. 6 upon 15. Very simple. Here we can write down 6 as 2 into 3 and 15 as we can write it down as 3 into 5. Now we can see 3 is the common factor in the numerator as well as denominator. So we can cancel it out, right? We are going to get 2 upon 5. Now, in order to make the exponent of 5 and 2 as same in the denominator, what we need to do, since 5 is having its exponent as 1, we have to make sure that we will be making the exponent of 2 also as 1. Now, this cannot be multiplied only in the denominator. We have to make sure that we multiply it in the numerator as well. So, this will give us 2 into 2, 4, divided by 5 into 2 whole raised to 1. Which will be giving us 4 upon 5 into 2 is 10. So, 10 raised to 1 is nothing but 10 itself. Now, 4 upon 10, it is nothing but 0. We tried shifting decimal point towards the left hand side one time. Okay, because we have only 1 0 in the denominator. Now, this is the final subpart of question number 2. 9. 35 upon 50. So, here what we will be doing, we will try to simplify first of all 35 upon 50. 35 can be written as 5 into 7. Whereas, we can write down 50 as 5 into 10. 5 is common in the numerator and denominator. We can cancel it out. We will be getting 7 upon 10. Now 7 upon 10, easily we can write it down as 0.7. Same reason, since we have only 1 0 in the denominator, right? So therefore, we will be shifting the decimal point only one place towards the left hand side. So therefore, we will be getting 0.7. So the only trick in all these subparts is we have to make sure that we will make the exponents of 2 and 5 as same, the largest one. Okay. So among 2 and 5, whichever is having the largest exponent, we will make sure that we will make the exponents of both 2 and 5 as the same one. And then we will try simplifying it in order to find out the decimal expansion without actually dividing that number. Exercise 1.4, question number 3. The question is, the following real numbers have decimal expansions as given below. Decimal expansions are already given to us. In each case, we have to decide whether they are rational or not. If they are rational and of the form P by Q, we have to tell what can we say about the prime factors of Q. So, understand the question carefully. We have already been given decimal expansion. We have to first of all figure out whether the decimal expansion are rational or not. If they are rational, definitely they can be written in the form of P by Q. Then we have to say that what will be the prime factors of Q, which means what will be the prime factorization of the denominator. Okay. Now, here, this is the first subpart of question number 3. 43.1, 2, 3, 4, 5, 6, 7, 8, 9. We can see that it is terminating, right? It is ending after a certain point of time. So we will write down it is, this decimal expansion is terminating decimal expansion. So, whenever we have a terminating decimal expansion, what kind of number it is? It is a rational number. And all the rational numbers we know, they can be written of the form P by Q. Now, over here, the prime factors of Q is of the form definitely in the prime factorization, we will have only 2 and 5 as its prime factors. So they will be of the form 2 raised to n into 5 raised to m, where the exponents of 2 and 5, which are n and m, they are whole numbers. So first of all, just check whether the decimal expansion is ending after some point or not. If it is ending, definitely it is a terminating decimal expansion. And if it is terminating decimal expansion, it is going to be rational number which can be written in the form of p by q. So the prime factorization of q will include 2 and 5 only as its prime factors. So it will be of the form 2 raised to n into 5 raised to m, where n and m are whole numbers. Now this is the second subpart of question number 3. Clearly we can say that looking at this decimal expansion 0.120, 1200, 12000, 124 times 0 we have, right? And after that we have 3 dots over here, which means it will not end, keep on going on and on. So therefore we can say that it is non-terminating. Definitely this decimal expansion is non-terminating, as well as there are no set of numbers which are repeating, right? So we don't have any pattern over here. We cannot see any numbers which are repeating after decimal expansion. So that's why it is non-terminating, non-repeating decimal expansion. So if it is non-terminating, non-repeating decimal expansion, so it is an irrational number. If it is an irrational number, we cannot write it down in the form of p by q, and that's why we don't need to worry about what will be the prime factors of the denominator q. Okay, so it is ending at this point of time only. So what we need to check over here, whether in the decimal expansion, is it terminating after certain point of time or not? If it is ending, then we will call it as terminating decimal expansion. If it is not ending, we have to check whether is there any pattern which keeps on repeating or not. In this case, we got that there is no pattern which is repeating, right? We don't have certain digits which keeps on repeating over here. So therefore, we will say that it is non-terminating, non-repeating decimal expansion, and hence all the non-terminating, non-repeating decimal expansions are irrational numbers. So there is no point of expressing it in the form of p by q, and we don't need to worry about what will be in the prime factors of q. Now this is the third subpart of question number 3. 43.1, 2, 3, 4, 5, 6, 7, 8, 9. Now observe here carefully. We have a bar over here. Above 1, 2, 3, 4, 5, 6, 7, 8, 9, we have a bar over here. What does that mean? It means that this decimal expansion is written in this way. 43.12345 6, 7, 8, 9. Again you will have this pattern 1, 2, 3, 4, 5, 6, 7, 8, 9. Again you will have this pattern 1, 2, 3, 4, 5, 6, 7, 8, 9, and it keeps on repeating. It will not end. Okay, it will not end. So clearly what can we see in this decimal expansion? It is non-terminating because it is not ending at a certain point of time. It is non-terminating and repeating decimal expansion. Because 1, 2, 3, 4, 5, 6, 7, 8, 9, this pattern is something which keeps on repeating again and again. That's why we have a bar over here, right? So it is non-terminating, repeating decimal expansion. And all the decimal expansions which are non-terminating, repeating decimal expansion, they are actually rational numbers. So we can say, since it is non-terminating, repeating decimal expansion, so it is a rational number which can be expressed. We know that rational numbers can be expressed in the form of P upon Q. Now, what about the prime factorization of Q? So, over here, Q is actually not of the form 2 raised to n into 5 raised to n. Definitely in the denominator of this rational number, you will have any other prime factor also apart from 2 and 5. So, we can say that the prime factorization of Q is not of the form 2 raised to n into 5 raised to m, and hence where n and m are whole numbers, so we concluded that from all these three subparts, if it is a terminating decimal expansion, it is a rational number. If it is non-terminating repeating decimal expansion, in that case also it is a rational number. Now, what about the prime factors of Q? So, if it is a terminating decimal expansion, the prime factorization of Q will be of the form 2 raised to n into 5 raised to m, which indicates that the denominator will only have prime factors as 2 and 5, not any other number, right? But whenever it is a non-terminating repeating decimal expansion, again it is a rational number which can be expressed in the form of P by Q. But this time, the denominator will have any other prime factors also in the prime factorization apart from 2 and 5. So, the prime factorization of Q in this case will not be of the form 2 raised to n into 5 raised to m, and hence we can say it is a non-terminating repeating decimal expansion.